Okay. LPC battery.
Hey, how do I change the feeds? What I'm doing here is not. Oh yeah. So that's a separate feed now. So just think of it like a third screen. Right here. If you move your email straight up from this screen, it'll go on the. So this is yeah. Pro. Yeah. So we might just shrink the video feeds a little bit, but whatever you feel is easiest for them to see. Yeah, check this out. This is really fun. I don't know but you can go through. If I just do that. Oh, sorry, I got you. So if I do this, choose the letter, you can choose which window to open the file. Xbox. Just double checking everything.
Right. Check, 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 check. Huh? Greetings, greetings. Greet. Are these on? Yes, they are. All right. Let's see. This is this one. Check, check one. Why is this so low? Your mic is low. That's why. But we're not going to get into that. We'll get into the fine details of that later. This meeting is about to start. Thanks for listening to the world's most last second sound check. Is everybody having a good time today? That's great. I was more expecting, yeah, not to see a thumbs up. This is not an improv session. I'm just doing my best. That's I don't know any jokes. Oh, that's even worse. I don't even know any appropriate jokes. All right. All right. You are operating. Check one. Check two. This is the second talk box. Oh, yeah. I don't know why. I'm just getting used to loving the sound of my voice. It's awesome. All right. We are good. We are good. I'm sure with the doors closed, you can hear everything. All right, cool. Oh, it really is. It really is. Just keep it separated. Hello, check. Hello. I am not a presenter. I am just a simple sound guy. If anybody needs any help with presenting your presentations, I have no idea if you should ask me. It's a bad idea. Hope everybody has a great afternoon. I'm going.
All right. Waiting for the doors. Thank you. Hello, everyone. This is another year of the Containers and Checkpoint Restore microconference at Linux Plumbers. And we've got quite a few talks for you today with a bit of a mix of in-person and online. Thankfully, most everyone managed to make it online. And what time is it? About 1 more minute. So For any of the people speaking, I did load whatever you sent to me. There is a laptop in front here that you can use to switch your slides. If you need any last minute updates to your PDFs or anything, please send them to me by email, and I'll try and update things in background, as we can do that this year without disturbing things too much. And so I'm just gonna get the laptop out for this one. Welcome LPCs. This one is not currently in the meeting on the program. Let's refresh. There we go. Okay. Forgot to check that the laptop in the room was actually functional. It's not quite, but there. Okay, that should be fine. All right, so you can come up for the first one. We'll just I'll switch the slide deck from my laptop and it should be good to go.
Just to describe my slides.
Otherwise,
if you
yeah. Which? Take present.
Okay, sure.
Okay, there you go. So you've got the slides, and you can just click like next here or something to move around. Okay, all good. All right.
Hello. So I've been working on adding page map scan octal in Linux. So we had some use cases, and along the way we found more use cases, and we came up a very generic ioctal. So we hope that it would be beneficial for other projects as well. So I'm gonna share the story, and then we are gonna share the use cases, and then how you can decide how you can use that in your own project. I'm Osama. I work for Collabra. I have Andre with me. So get write watch and reset write watch are Windows APIs. These APIs are used to get and clear write tracking state in Windows. So they can work on any kind of area. So sometimes they need only specific pages from a whole larger area of memory. And also this API has wide use cases. For example, copy on write mechanisms or security intrusion detection or garbage collections on Windows. So we want this to work on Linux by some translation. So translation can be done in some ways, which can be considered as user space mechanism. For example, mprotect and segmentation handler. So you just write protect a specific memory, and in segmentation handler, you do the bookkeeping that which pages were written to, and we resolve the faults, and which pages were not written to. So, and we can also do this by user fault FD. So you register the memory area with user fault FD. And when there is some fault happens, you get a message over the user fault FD, and you can resolve the fault and do the bookkeeping. But there, as you know, there are signals traveling from kernel to user space, and so this would be this is very slow, and also this has some implications. For example, some software layers don't like write protected memory, so it creates problem for some use cases, and also some workloads are very demanding. So this create problems for them as well. For example, games is a good use case for that. So initially we thought let's go with soft dirty, which is already present in Linux kernel, and a lot of other projects are already using it. So soft dirty flag is a combination of PTE flag and VMA flag. And operations which were possible was that read operation is possible. You can read the flags, or you can clear the entire process of that flag would be cleared on entire process. So we needed more operations. And also kernel's activity was affecting it. For example, one VMA, which is non-soft dirty, could get merged with soft dirty VMA, and entire area would become soft dirty, which shouldn't have been. And also this is historic, that why it is what it is. Like when they were implementing this feature. So they had this idea that there shouldn't be separate VMAs for soft dirty and non-soft dirty VMAs. So the shortcomings are that it is not accurate. Atomic get and clear operation is not possible because page map is a file, right? You need to write or read at one time. And soft dirty flag or on a part of the memory cannot be cleared.
So originally, soft dirty, it was created for Crew. In Crew, we have one of the features that we have, it's live migration. In case of live migration, we want to do the full memory dump, and on the next iteration, we want to dump only the memories that have been changed from the previous iteration. And this is why we implemented soft dirty. It's a memory tracker, and it was created 10 years ago, and at that time we didn't have user fault FD. We didn't have any other ideas how to implement a memory tracker, and we want to implement it as simple as possible. Because it's sort of hard to push something in the kernel that has only one user for this feature, so it should be simple. And as for downsides, that it's not atomic, we have problem with some VMAs that can be merged. All these downsides, they're not so critical for Crew. So we use soft dirty for many years, and it just worked for us. That's it for now. And
so we created a prototype ioctl based on soft dirty, and in that prototype we decided that we will just ignore the VMA part of PT, VMA part of the soft dirty flag, and we should be okay, because kernel at that moment was setting PT soft dirty flag regardless if it was set on VMA or not. But when we are just coming up prototype, we had sent it upstream, but we found that it got broken because of something else. So they stopped setting PT flag if VMA flag was set, because no user was affected. So we couldn't do anything. So at that moment, we tried that let's fix this soft dirty sport over VMAs. It was kind of a idea where we will just keep record of those areas which are soft dirty. But this was increasing the size of VMA, and that is frowned upon. So finally, community came to help. So Peter Zhu recommended me user fault FD. Initially, I was skeptical. So this is something else, how we are going to use it. But user fault FD had write protect flag already, but it was we needed to resolve the faults from user side. So we came up with that, let's make it asynchronous. So if it would be a specific mode where user will, kernel will resolve the fault automatically. So it really helped us. And soft dirty would be the opposite of the write protected. But then we found another problem that some PTE none or empty pages were not storing the state that this page has been write protected. So we added another feature in user fault FD, write protect unpopulated. So it started using PTE markers to mark those 0 pages. So page map ioctl came into life finally, where we were using write protect flag instead of soft dirty flag, and input was being given as PM scan arc, and we kind of tested it a lot in different use cases. A lot of other community suggested things. So we started returning data as a compact structure in form of ranges with specific flags. For Windows API emulation or translation, we needed max pages, so that how many pages we want to find in this area, and then we just want it to return. And then we implemented all of this scanning functionality for all memory types: pages, huge TLB, and holes. So supported operations are, you can perform get operation if output buffer is specified. You can write protect a specific memory area, and you can abort the operation if no area is has write protect async enabled, because before using this ioctl, you will have to use user fault fd's write protect async and unpopulated as required. So these measures were necessary. And we added filtering support on the request of Andre. So initially I said that our ioctl is the generic ioctl, but it was not that generic. So he suggested a lot of things like which we implemented, for example, filtering support inside the kernel. So we will give kernel a specific requirement that we need these pages, which this flag set and this not set and that. So all of this mess just supporting that. So and page map supports a lot of flags, but we have decided to support only those flags inside this ioctl which are needed, which have some use case. For example, page is written is the original use case for us, and then others are for CRIU. So initially it had good performance overall as if we compare it with the user space solution, but still it had a lot of room of improvements, like which I initially was saying that no, we don't need to improve it further, but by testing and by help of others like Paul Guffman, so he helped find out that no, this could be improved way more. So we done multiple passes to make code more simpler and more performant. So when we were write protecting pages, we done that on our end instead of using whatever user fault FD was using, and we started flushing TLB only once. So that was very expensive, and we started using less temporary memory inside the ioctl because data cannot be written to buffer from inside when you have taken a write lock. And also we reduced the page walks. So benchmarks were astronomical, as you can think, like we are comparing user space solution with a kernel space solution. But overall, the real win here is that we are doing things. We have we can do all those things which were people doing by reading page map file. They can do by ioctl way faster.
And a few words about the new interface in Crew. The main interest of this new interface is how to effectively handle pages that we need to dump. Because before this new interface, we used page map, but page map, in case of page map, if we want to know some information about pages what we need to dump, we need to read information about all pages in a memory mapping. With the new interface, we can do some filtering inside the kernel. We can request, okay, give me just pages that are present or swapped. It's actually the pages that we need to dump. We don't need to know what file pages we have. We don't need to know what pages, like 0 pages and so on. So the new interface is much more efficient in terms of queue because we don't need to read a lot of information from the page map file, and now we can just send requests to get all pages that we need to dump, and we get not like information about separate pages, we get regions that the memories that should be dumped. Another good thing about the new interface that we can detect 0 pages. We need to know information about 0 pages when we are doing pre-dumps. For example, if we dump some pages on the first iteration, on the second iteration, if we detect 0 pages instead of pages that we already dumped, we need to like remove these pages from the parent images to save some space on the disk and this stuff. The problem with zero pages that with the page map, we use a physical address to detect zero pages because all zero pages will have the same physical address in the kernel. So to detect zero pages, we create a new mapping, read physical address for like zero page that we know that it is zero, and then we use this physical address to detect zero pages in other mappings that we're going to handle. And as for the new memory tracker, we're going to support it in the crew because I don't remember. I think we have some problem with unprivileged mode in crew and soft dirty. And we can use a new tracker in the unprivileged mode because the only thing that we need to be able to create is user fault FD. And I think by default, user fault FD, we have a sysctl that control whether unprivileged process can create user fault FD or not. But if it's enabled, we can use this memory tracker in unprivileged mode.
Yeah, so Andre benchmarked page map scan ioctl on his end, and he also found quite some good benchmarks and a lot of speed ups between different iterations of the dumping. Yeah, so now we should think that what could be the more use cases. For example, if there is something which is using page map file already, so you can use.
This work with advise page up. That would be nice if you could just do a scan and say advise page up where the PT is present, you know, just a simple filter like that, rather than having to use the process advise. So a process advise, it takes a PID and then it takes like some virtual ranges, which is unfortunate because then it's a two-step process. You're looking at proc maps and deciding what you want to do. But if you could do it through page map on, it's just keeping a procfs interface. So rather than having to use a syscall interface for process advise.
I mean, if you already can do this stuff with syscall interface, we do not want to duplicate the same.
It's doing it in one step rather than two. So it's basically saying rather than going and parsing process maps and then hoping mappings haven't changed when you turn around to try and use process advise, you do it in one step where you say you're already walking all the VMAs. When you find the things that match this filter, page it out. I don't know. Just the thought.
Okay, just maybe we can introduce a new like way to.
Just a thought. Yeah, I've never been happy with the process of advise page out interface. So that's why I bring it up.
Thanks. Oh, thanks. Any particular reason why you can't use the hardware databit? Which means you don't have to write protected pages, you don't have to take page faults. And some modern CPU, I believe, have some particularly effective way of batch collection of hardware databits, at least for virtualization, maybe not for user pages. But I mean, that's something KVM has been doing for a long time for migration, for example, or for even tracking the VGA frame buffer. Why can't you use a hardware databit? Flush the existing one into the struct page to clear it, and then use the actual hardware databit. Is there a particular reason why you can't do it?
Sorry, can you repeat the question?
Sorry. Is there a particular reason why you can't use the hardware dirty bits, the real hardware one,
Okay.
instead of write protecting the pages? And so you don't have to take page faults.
So both are very different. So the idea here is that so hardware dirty bit is managed by hardware, right? So here,
Set by hardware, it's cleared by software.
but here we are looking at different perspective. That, for example, any piece of software just want to know that which. So there is an area of, let's say, 10 pages. It want to dump only those pages which are changed. So you can use the simple this API. This is so that which pages are dirty, you can just dump those instead of hardware dirty bits.
I don't understand. I mean, you currently are trying to emulate the hardware dirty bit by taking page faults. Why can't you just use the hardware tells you specifically those pages have been changed? So, and you don't have to take page faults, right? So. Yeah, but that's okay. You can transfer the current dirty bit into the struct page, and you get a clear dirty bit, and then you can use it from there. I mean, you probably still need some changes to the VM, of course, to collaborate. But it seems to me like using the hardware the way it's meant to be, and would avoid the cost of the page fault.
Yeah, I don't know much about this, but this solution was suggested by Peter from the Monkey. So
the fact is that your API exposes the fact that under the hood you are doing the right protect the page fault is what bothers me. It means that we can't then, in the future, for example, improve it by using the hardware dirty bit instead and completely remove the page faults and write protection. The API, I think, exposed too much of the underlying implementation instead of having a higher level of API, which is tell me what's changed. And so in the future, if with some collaboration with the VM, we can actually make better use of the hardware bit and make something even more efficient, faster, we're going to have to change the API again. This is my concern. But
so just
we don't expose when we're using faults on.
Well, you do call it WP by protect. So okay, you expose it at least during the name of the flags you're passing. But yeah.
So just like VMA struct, you cannot add anything to page struct page very easily. Like
but it's already there, the dirty bit. You just flush it out. Like what the VM does when it harvests the dirty bit today is it takes them from the PT and copy them in the struct page. And that means you can start. If you had already a dirty bit in there before you started the tracking, you can do that to clear it out. And from then on, you can actually rely on the dirty bit. Anyway,
I'm not sure about. Okay, so many thanks to the community, Andre, Andrew, Michelle, Paul Guffman, and Peter Zhu at helping at different point in times. Thank you.
We've got about 2-3 minutes if there are any more questions or discussions at this point. Yep.
So I think the soft dirty bit in Creo is hardware dependent, right? It doesn't work on ARM as far as I know. Is this hardware independent?
It is hardware independent, but I'm not sure if it is implemented for ARM.
So if this user ported the feature and red bucket be supported or not, so we need to work on.
Okay, yeah.
So it depends on user port.
Yeah, because the pre-dumping doesn't work on ARM right now on Creo, I think. Yeah. Okay.
Thank you.
Okay. Thank you.
I just got a couple of minutes, so we can just wait. Alex, can you just confirm in the chat that you can hear us fine and that you'll be able to answer some questions?
Yep. Hello, everyone. I can hear you well. That you can hear me too.
I even see Alex as unmuted, but I don't think we can hear him.
Okay. Okay, attempt number 2. Hello, everyone.
Yeah, I don't know if it's a microphone issue on his end or on our end. It's not super critical for this presentation because I'm mostly going to be speaking and you can answer through the text chat, so that's fine. It's going to be more of a problem with a later presentation that he is giving. So. Anyways, it's time. Hello, everyone. I'm Stefan Graeber. I work for myself these days. I'm not at Canonical anymore, but I am presenting work that Alex has been working on for a bit, and it does work at Canonical. So it's the two of us. Alex is unfortunately stuck in Germany because of visa problems with the US. So I've got the honor to actually go and give the actual talk. All right. So what are we trying to do? Some bit of background around this. For anyone who's not familiar with how the user namespace works, and I don't know how many of those that might be in the room, which I'll see, the user namespace, sorry, the user namespace maps a UID and GID or set of UID and GID between the namespace and its parent. So in most cases, the parent is the host system, but it could also be another namespace, and you can nest those things. Most container runtimes that use the user namespace will map 65K UID and GID so that mostly trying to get POSIX compatibility, making sure that nobody no group is mapped properly. And yeah, just trying to make things mostly work. That's been done for a while. Now, a common pattern in some of those container managers is to map non-overlapping, so effectively create non-overlapping maps. That means every single container on your system gets a minimum of 65K UID source in kernel to be owned by a different UID and GID. And they just keep on going. Like you can have processes on by that, and it works just fine. Where it gets fun is when you need to actually have anything persist again, because you need to go through the file system. But that's where the ID map mounts are magical, and we can just say that, well, within this namespace, this range of UIDs and GIDs are mapped to this range of UIDs and GIDs on the host, and go and send you right through it. So that's made things quite simple, quite nice. With this concept, it allows for effectively any user on any system to get an entire range of valid UIDs and GIDs inside of a user namespace that they create just as themselves. No set UID thing, no help from a privileged process. And that's what we'll show very shortly in a demo. And we'll get to the actual kind of set of changes and stuff. There's going to be like a QR code linking to the patches, but as much as I was extremely scared by that proposal originally of like, oh, we're going to have to change just about everything in the kernel. As it turns out, we didn't, which was a very good surprise. So that's a bit of the slightly more nitty-gritty of how this stuff was done. So as mentioned, the general idea is KUID and KGID type have been changed from 32-bit to 64-bit, where half of that is used as a user namespace identifier. There are a few extra changes that were made to allow for controlling that, which is currently a simple text file that you can write to, and that just turns the thing on for the given namespace you created. It's very similar to the set groups API, and there were just a few of the normal KUID, KGID helpers that needed some tweaking around that, and similar changes were needed on the VFS ID map side to also handle that properly. So that's kind of the rough idea of how that stuff has been done. I'm just going to go through a quick demo to show what things look like today. So let me just make sure my terminal is all set up here. It is, and I should be able to do screen share, allow, full display, share, and yay. All right, let me just zoom the head of this stuff. There we go. Hopefully that should be fine. Okay, so I'm going to start with your box standard user namespace and a very easy way to create one. So fork, remap UID 0 and GID 0 inside of that namespace to the unprivileged user outside of it. And then user namespace enabled, mount namespace, network namespace, bid namespace, and please don't mess with my mount propagation, effectively. That's what all those flags do. Okay, you do that, and you get your usual, hey, I'm root, but not. So you're root. But if you go look at the actual map, you can see there's a single UID and GID here. It's root. It's mapped to UID GID 1000 outside of it. All right, cool. I did write the simplest piece of C that I'm capable of writing, pretty much, which is called set ID. It's effectively SU minus all of the PAM stuff. So all it does is it changes your GID first, UID second, and then execs bash. That lets me do something like this, where I can do 1, 2, 3, 4, 1, 2, 3, 4, and it tells me that I should go away because I'm inside of a user namespace that only has a single UID and GID mapped, and 1, 2, 3, 4 is definitely not valid in here, so go away. That works as expected. But now we can do this. So just echo yes in isolated user namespace. It doesn't change the map. So if we go look at this stuff, nothing has changed. It just has changed the behavior for anything outside of the map. So now if I go and do this stuff again, hey, correct. And sure enough, my UID and GID, everything is set properly. Now, there's an obvious issue with this. Like if I here has my fake root mapped to my actual unprivileged user, I can totally create a file, works fine, no problem there. If I try and do the same thing from here, well, this is a whole lot more fun because there's no file system map or anything in place, so it's gonna just fail. And that might actually be fine for many cases. Like, well, I'm not gonna do any demo of the VFS stuff because there's actually some issues in that test kernel. But like you could totally mount a temperfest from inside of that user namespace, and then that user would be able to be represented on that and write through just fine. Same thing if you do a fuse mount at that stage, like a fuse mount that originates from within the namespace would be perfectly valid for that random user. There's no problem there. The only issue is when you interact with outside of the user namespace, And for that, well, we've got Christian to thank for the VFS ID map stuff, because that's how you do that. So now if we want to have some fun, we've got that process, so that bash process running here. Now let's look at what that looks like from outside of it. So we can see bash is running here. As far as what shows, both of them show running as Ubuntu, so UID 1000. The reason for that is what we've done is when looking at the UID from anything outside of the namespace, we can't represent this thing. It's just not possible. So what we do is we pick the owner credential from the user namespace, so whoever created the user namespace effectively, and that becomes the owner for anything in the process tree as far as what shows in traditional fields. Now, there's some way to actually go and get more details. So if we go look at proc, this file, and status, and we go through this entire mess, we can see, so UID and GID are your standard ones, but there's also isolated UID, isolated GID, which shows you the value inside of that isolated user namespace. So if anyone cares, they can figure it out. There are a lot more edge cases around that for like other ways that UIDs and GIDs are being sent through right now, which will be translated the same way, but where also having some way to get the actual thing would be interesting. So that's roughly how that stuff works. As mentioned, I can't really do the storage demo right now. It's some issue with that test kernel, but we did make it work, just not in this build. And it uses VFS ID map, or you can just do a mount directly inside of that user namespace, and that works as one would expect. So if I go and share my screen, we're back to slides. There we go. So there is a QR code for anyone who cares to go look at the patches. If you scan that, you're going to see the 11 or so patches that were needed for this work. It's also listed, I think in the slides themselves, there's like a bunch of links at the end that will have that. So what's next, other than fixing this kernel build so that the VFS stuff functions? Well, the main issue we currently have is that it requires root to be a real UID. That's kind of fine, but that's also the one user I really don't want to give a real UID to. So we're looking at fixing that particular one so that you don't need to. You could totally create a user namespace with no map set whatsoever, then set this flag to yes, and then switch to whatever user you want on there, and that should be working just fine. And again, if you want anything to persist, then you're going to need the VFS ID map to sort that one out. There's some more integration bits with the VFS ID map that's going to be needed. I know that Christian is quite keen on kicking out any reference to the user namespace from a bunch of the ID map stuff in the kernel, which is going to make this particular patch set a bit longer, because there's not going to be any obvious way to get to the user namespace and get the stuff we need. But I mean, nothing that can't be worked out. And mentioning kind of some of the other corner cases and areas where things are being sent through. SCM creds was one of those that came to mind, where you do get UID and GID that way. In this case, you would get the UID and GID of the namespace owner, but it would be nice to have additional fields in there as well, so that you can tell, okay, well, yeah, that's the own. Clearly, this is coming from a user namespace. That's the owner as far as what's represented on the host, but inside is actually this user. Because we've seen occasionally like daemons and the like on the host wanting to know whether it came from a root user inside of a namespace. It's always a bit risky because like this is possible to do. You can easily get that information. You should just not assume that this is any kind of proof that this user is privileged in any way, because it's not. But that's still something there. The other thing that we're looking at still is kind of handling of all of the nested stuff. So obviously wanting to get that in, like, it should be fine. Like you should be able to be inside of a user namespace and just do this. And that's not a problem because we don't strictly need those things to be hierarchical in any ways in the kernel. It's just like a random ID that's used for this. And that's kind of mostly the idea. I'll actually go and click. Let me see if I can actually click on the darn thing. That would be nice. I have to go through the patches real quick. Let me just open that up here, and I can screenshot that part. Yeah.
Is it okay if I?
Yeah.
Wouldn't it be better if you disallowed writing ID mappings completely to isolated user namespaces? Because I thought it was also the original idea.
Yeah, I think I'd be actually quite fine with that. Like the reality is that once you do have VFS ID mapped working anyways, you don't really need to map anything to a user of actual value. So that would actually avoid potential issues.
Not just that, I think it would be cleaner for user space if they saw, okay, there is no ID map written, and yeah, it's just, I think it makes the implementation cleaner and just keep the ID mapping part completely out of this. It's essentially a new type of user namespace if you're being honest.
Yeah, we're gonna have to think about whether there are some corner cases where you might want to, whether it's shipping an FD across or shipping something across between the host and a user namespace in that mode, where you would actually need to have a UID that can be resolved for that. I definitely want to make sure that we don't need one because, especially for root, that seems wrong. And I would definitely I don't know that we necessarily need to block it, but it definitely should not be the default in any kind of examples or anything. It should be if you have a weird need where you actually do need the user to be mapped to something on the on the parent level, then you need to go and write a map, not always write a map unless you don't have enough things. Because what I don't want to see is container managers mapping the first 65K UIDs and GIDs, and then just using that for the overflow, so for anything past the initial 65K. Because that's going to be extremely confusing. It would work just fine, but it would be really, really confusing to see, I think. There's Tycho wants the mic behind you.
Yeah, thank you. Can you just talk through how the mount stuff would work, how that mount mapping would work? If I am trying to write from somebody who isn't mapped,
right,
what happens?
Oh yeah, I can show you that, but easily it fails. I mean, I think I did it all right.
It does fail. You must have a solution that actually works.
Right. So so that's why you use the VFS ID mapped mounts, where you effectively tell the kernel, hey, this path there, I want it to be mounted kind of as a bind mount to this path, but now any write from UID 1234 in my case needs to be mapped to either straight up UID 1234 on the host or be mapped to whatever you want. And
so there's no anonymous namespace or isolated namespace like this for ID map mounts.
Right. No, because ID map mounts need to be mapped to a real resource. Yeah.
Okay.
Yeah. Yeah. So that's the part where you do need something privileged to put that in place.
Sure.
The cool thing is that in theory, in many cases, you might not it's possible to create a unprivileged container manager that would use this and not need anything privileged whatsoever. Because so long as you just use either you create a temperfest, you unpack everything, and you pivot to it, or you use a Fuse implementation of the OCI Larry stuff, you will also get a root file system out of it that you can pivot to. And in those cases, you don't even need any ID map to anything because you're effectively just running everything ephemerally inside the container. You would just need something like an ID map if you needed to pass through a /data storage thing to actually read and write data through.
Yeah, I guess what I'm wondering is can I get away with not ever mapping anything with this? And it sounds like no, I'll always need to map the file system.
Yeah, you would. Yeah, unless also unless you can originate just it from a Fuse mount from inside the user namespace or a temperfest from inside the user namespace, those would be perfectly fine. In theory, network file systems that also support the user namespace would similarly just work.
I see. Okay, thank you.
Yeah, thinking my user could see the file system, it was just seeing it as overflow, whatever. So you could only see anything that had the other permission bit set, which can be good enough. I mean, we've seen cases with web browsers and other tools where it's quite valuable to be able to have every one of your rendering threads or whatever run as different users so that they can't attack each other or that kind of stuff. And that would make it really quite easy.
Have you looked into possible interactions with LSM hooks? I just remember this from the work that I did for the ID map mount stuff, that the LSM hooks were the part where all of the nastiness lies. I think I fixed most of that for ID map mounts, but there is stuff like Tomoyo that looks at UIDs and GIDs and has like weird rules in user space where you can restrict based on UIDs and GIDs, and any stuff like that probably would need some.
Yeah, that's
Okay,
going to be an
or you might
interesting
approach
one
it
for
with that.
sure. I don't know if Alex looked into that. He can comment in the chat since I think his microphone is not behaving right now. But it's definitely interesting. And the question would be then, what is exposed to the LSM hook? Do we expose the same as user space, which is just the owner of the namespace, or is it because they are in kernel, they actually do get to see the entirety of the thing, and they can distinguish like, oh, actually this is root, but like inside of that namespace. So I think it's going to be interesting to look into that. I don't know how that works today, given the kernel
you hear
works.
me?
I just don't know which of the two code paths they're getting, whether they're getting the full 64-bit KUID, KGID, or if they're getting the subset that's effectively filtered to just be what's exposed to user space. Hopefully Alex knows and
Yeah,
can.
you have more
can
fun
send-
because now I just saw a talk in the eBPF session about LSM hooks from BPF, where they implement, for example, safe set UID or like UID and GID transition rules in BPF programs, and they look at KUIDs directly. So you
yeah, so in those cases, they would see the 64-bit thing, which would, I mean, that's kind of always the thing with eBPF, right? Like you effectively build it using kernel internals.
It's not your issue.
Right. Yeah, I mean, it is built with kernel internal. So in this case, yeah, it means that your eBPF program will have to deal with not seeing 32-bit anymore, but seeing 64-bit, and either calling the helper we have to strip the string, strip whichever half you don't care about, effectively, or just actually look at the whole thing. Yeah, it's definitely going to be interesting. I think there's a bunch of other interesting kind of edge cases around that.
Yeah. Now that I think about it, like the safe set ID LSM would be kind of interesting how it interacts with. I don't know how it interacts with user namespaces, but in this case, it would be interesting if you want to restrict setting to UID 1, 2, 3, 4. How this would work with isolated user namespaces. They need to be taught probably to work with this.
Yeah, and I see that Alex is currently typing. Can hear the question,
can you
but not
hear
sure
me?
if you can hear me. No, we can't hear you. So that's why
Oh.
like you need to type in the chat, and we can read that. We're gonna have to figure out the speaking part before your talk. So I was just gonna yeah. So that's the current patch sets effectively, which I don't think we've got a diff stat ready, but like I remember the diff stat being surprisingly small. Like I was really worried when we started doing that it was going to be the same as when the user namespace got introduced, where pretty much everything in the kernel had to be modified. But thankfully, between the work that was done with like separating the ID map and all that stuff for the BFS work, and just the fact that everything's using pretty much macros and functions kind of all over the place, it was a much smaller patch set than was expected, and was really good to see.
If it still have a chance at being merged, it needs to be really small because I
Exactly.
don't think anyone is keen on.
No. Yeah, and it was kind of that's why we wanted to do this proof of concept to get an idea for like, okay, is this insane or not? And currently, we're like on the it doesn't look completely insane category. Obviously, the next steps are gonna be well, refining the patch that actually works properly. The fact that we saw a regression when testing things today was a good indicator of we need tests. So that's going to be another thing that needs to be added. And then sending some RFCs on the containers and LKML list to get some more people to look at them, poke more holes in there, and also get a better idea of kind of what's the minimum set of things to be to have this be included. Like we currently don't see something like SCM creds extensions as being needed in the initial pass. Like this is the kind of thing that can be built on top and added later on. So, and we can see Alex's camera, but oh, and it did right. Seen that he has seen the SafeSet UID LSM thing, and oh, actually, I think we just got some noise from your microphone, Alex. Maybe. So you might want to try that again. Oh, there we go. Yeah, we can hear that.
Okay. It's interesting because probably the turning on the video helps to get microphone working. Okay, hello everyone. Yeah, I have listened to the questions, and yeah, I have definitely seen the safe UID stuff, and I have make it just to work properly with the old in the old approach when the UID is mapped. to properly handle this extension to 64-bit. But for the completely isolated user ID, it just ignores them for now. And also this LSM, as far as I remember, it was a few months ago, it only works with the UIDs on that mapped to the host. So it does not handle anyhow the user ID transition inside the user namespace. So all the rules is relative to the host. But yeah.
Okay. It's not even it's not even current user namespace aware in any ways. It just always shows you the host's value KUID. Well,
As long as you can't really load safe set ID rules from containers, it should be fine, because you then essentially just restrict what host UID you can set UID to, that which should be fine, I guess.
Yeah, it should work because we have all the UIDs mapped to the host, but it means that all rules that we write to this LSM will be relative to the host UIDs, not to the container ones. If I not miss anything there.
It is kind of interesting, Todd, that indeed with eBPF being so widely used these days, a bunch of those programs are going to have a fun day when something like this lands, because anything that's loading an eBPF program that compares UIDs and GIDs, like, since they're seeing the kernel side type, not the user space side, they're going to see the other one. But I mean, that's what you get for using eBPF. Like, that's the whole point of, you've got access to those kernel internals, so it's true there too.
The issues, we just had this discussion before, and there was a patch set a while ago where they wanted to set X adders from BPF programs, and then you run into similar issues where you can set POSIX ACLs or FS caps that store UIDs and GIDs,
right.
And if you don't have the right context from a BPF program, you know.
And I think you wrote the code to translate those in Nextday, right? That was not exactly trivial to like pull the binary value of those things and like do all the rewrite and shifting and stuff. It's a bit of a pain. So even if they did know what namespace it is, actually writing the right value to the X adder is not trivial. All right. Well, we're about to run out of time. Thanks for all the great questions. It was definitely very appreciated. We're gonna, as I said, we're gonna try and get RFC patches out pretty soon. The patch set is surprisingly nice and easy to follow. So hopefully we can make some progress on that. I would love to see some kind of first pass of this, getting merged in the next year. So that'd be amazing. If you've got any more questions around that, well, feel free to reach out to either myself or Alex. And thanks a lot. All right, so I've got the slides loaded here. You can just click next here to switch, and that should just work.
Okay, great, thanks.
Bye.
All right. Hi, I'm Avery. I'm a first-year PhD student at Duke, and I worked on this starting during my undergrad at Columbia, and then after graduation over the summer at IBM Research with George, James, and Hubertus. And today we're going to be talking about containers, specifically if we should trust them. So containers are very popular. They're very scalable. They're very lightweight, but right now we currently trust them blindly. And so the work that we did over the summer was to extend a chain of trust from hardware up to each individual container instance. So I'm going to be going over now how this chain of trust is built. During the boot process, each component is measured. to verify the integrity of each of the software components during this boot process. These measurements are a cryptographic hash of each software component, and they are recorded in TPM registers to allow for verification. The TPM is a trusted platform module. It's a piece of hardware that is designed to secure the platform through artifact storage. The TPM also has burned-in keys that allow for the identity of a platform to be verified. But in particular for this project, we care about these platform configuration registers, the PCRs. There are typically 24 PCRs per chip, and these allow for the secure storage of values. And so we have, throughout the boot process, we have each hash is recorded. The OS and firmware can change the values of these registers through PCR extension. And so a PCR extension is taking the value currently held in the register, concatenating it with the value that needs to be added, and taking the hash of this and storing it back in the register. So through these platform configuration registers, you have a chain of hashes that can then be replayed to verify the integrity. And so Linux IMA aims to extend these measurements throughout runtime. So the goal of IMA is to extend these measurements and detect changes in file integrity, whether that be malicious or accidental, through measuring applications when they are executed. These measurements are measured and then recorded as well in the PCR, as well as recorded in a log. And so using this log and the TPM quote, you're able to have this non-reputable log of application measurements from the initial boot measurement through all the applications that have run on the system. And so using these measurements, we can then build trust in remote environments. Given the boot measurements, the application measurements, and the attesting machine can prove to a verifier and attest to its own system integrity. This is done through a TPM quote or any other evidence that the attesting machine gives to this remote verifier. And then the verifier will contain some sort of policy engine that then is able to make a decision given this evidence on the integrity of the machine. Once this decision has been made, it can give secure payloads, send keys, because we're building trust in this platform. And so what happens when we add containers to this picture? So IMA still measures these applications. These measurements are still being recorded in the logs. They're being stored in the TPM. But there is a need for namespace support here. Which of these measurements are coming from a container? You can't tell which of these applications is being executed by a container versus on the host. There's no isolation of these measurements. There's no way to tell them apart. And so our preliminary approach for extending this chain of trust from the hardware to the containers is extending Linux IMA to containers. We do this using eBPF. We actually hook into the same LSM hook that IMA does to record its measurements of the host measurements. And so we load an eBPF program, attaching it to the LSM hook mmap file. In this eBPF program, we record the namespace of the caller of nmap that mapped the file as executable. And we pass this to a kernel module that we wrote that then measures the file that was given from the eBPF hook, namespaces this measurement by concatenating the namespace ID with the hash of the file, and stores this in the host IMA log and extends it to the host TPM PCR. And so this IMA log will look like this. We now have the namespace measurements being recorded on PCR 11, and they are stored with the namespace ID as well as the file name. And so now we have a way of associating which of these measurements came from a container and what did these containers execute, as well as the hash of what the executable that was run. Yep.
Those who are reading impaired from this distance, would you mind reading out how this differs from the other?
Okay. So if we look at this previous, we just have the file names. And so there's no way to tell if this is executed by a container versus executed on the host.
How have you changed it?
And so we record the namespace ID, and then we can associate each container with the namespace that it is running in, and then connect what is executed in the containers to the measurements that we log.
Okay, thank you.
Okay.
Are the ones without namespace ID?
Yeah. And so when we look at attesting these containers, we're going to need an allow list of hashes for each container instance that's running on the machine. And so this is fine when you have a few containers, but containers are scalable. We don't want to impede on their ability to scale by enforcing attestation on them. So when we look at scaling this system, these allow lists get out of hand. It becomes infeasible to have this lengthy allow list on the verifier to enforce policy on each of these containers. We're also adding to a log that's already quite large. And so from here, we were pivoting to how can we enable container attestation without infringing on scalability and without adding too much overhead to memory. And so we went to measuring container images rather than individual container executables. And so given this picture, we have two containers running on top of the OS. Each of these containers are isolated by namespaces, C groups. And so we're looking here, what from the operating system level do we know about these containers? When they're created, when they're running. From IMA, we were able to check the namespaces of the container, but when you're in the kernel just looking at this container creation, how can we get visibility into this process without making extreme changes to the kernel? And so we looked at unshare. And so we were looking at when this container is created, unshare will inevitably be called to dissociate parts of the process that will then become the container's execution context. That'd be the namespace, the file system, credentials. And so when we're looking at Podman creating this container, we have a call to run C, which then calls the system call and share, which passes us into the kernel context. From here, we can gain visibility into this process. And so our solution adds another eBPF program, which hooks into cred prepare, which is called by unshare. And so from this eBPF program, we have another kernel module that, looking at the task that is calling unshare, the file system of that task is the container image that is being run. And so from this kernel module, we are going to create a measurement of this container, a single measurement for this entire image, and store this in the IMA log. So we have one measurement for the new namespace. And so when this container is created, the operating system measures the file system and stores it in the IMA log, extending this to a PCR value, so then the integrity of this container can be verified remotely through looking at the container hash that we've created. And so this container image digest, because we're working with the file system, we are traversing the file system to create one single measurement. And so we are doing a traversal, concatenating each of the measurements together, and recording the root hash from this file system traversal as our container image. And so given this one single digest for the entire container, we can then store a single hash identifier for this new container. And so when we're looking at extending these IMA logs with image digest, here we have a standard IMA log, but if you notice, we've started a container. This is its namespace, and we've recorded its file hash. Here we have a much smaller footprint on what we add to the IMA log, but we have this measurement for the container that we can use to build trust in its the container instance. And so when we're evaluating this overhead, this is run on a machine that has a hardware TPM. And so the overhead is large, but not as large as you might expect, considering we're creating a hash for this container image. And so now that we have this container image that is based off of what we can see from the file system, the container image digest that we're given from container repositories is going to vary quite differently from what we're able to have insight and visibility from the OS. Current container image digests are dependent on image layers, manifest files, container IDs, creation time, all of these things that we don't have any visibility from the operating system. But in order to build trust in these container instances, we need to have a container image digest that is measured in the file system and stored in trusted hardware so that we can verify these containers. And so to have these kernel verifiable image digests, we need them to be provided to extend this chain of trust and to enable this verification, because otherwise we have two kind of disparate image digest, one that can be verified by, let's say, a Kubernetes or a Podman or a Docker, and one that we would need to be able to build trust in these instances. And so just to summarize, this project explored building trust in containers, starting out by extending IMA using eBPF, and as well as measuring image integrity also using eBPF. So if you notice, both of these solutions utilized eBPF, and so they don't require any changes to the operating system kernel. We're leveraging kernel modules and eBPF. Eventually, we would hope to move this into the operating system, as eBPF programs are not measured, and so this provides a gap in the trust as well. But through this, we're able to measure container image integrity from the operating system. Yeah.
So just a quick question. So you need to traverse the entire thing, hash absolutely everything. That was still pretty fast. I'm guessing the machine probably was on SSD or something reasonably fast for I/O. Also, doesn't that completely trash your VFS cache?
It depends on the size of the image.
Yeah, that seems not exactly ideal. I don't remember who had their hands up first, so we're gonna go Taiko there and doors back.
Two questions. First, do you include, like, modification times and stuff in your system? And then second, if I understand correctly, the measurement in the TPM will depend on the order in which containers are launched?
Yep.
Okay.
Yeah, and so we're able to, because we're recording them in a measurement log as well as extending them to the TPM, we can use this measurement log to replay the value that was recorded in the PCR to ensure the integrity of the log, which is why we can trust what's in the log.
Okay, and you do include timestamp?
Yes.
Okay.
Oh, no, we don't use timestamps in the containers. We only have, from the operating system, we only have visibility into the file system. And so we don't have.
So you don't have like the file, like modification time of the file, or do you?
We're currently not looking at modification time.
I don't
know. What happens if you have to relaunch a container for some reason, because the PCRs and the order matters on what you're testing and measuring, right? So have you thought about how you can solve that?
So if we're relaunching a container.
Yeah, if you have to restart it at some point, you measure it again, your SAT56 will change, or if you launch the containers on a different order every boot, you'll end up with a different log.
You'll end up with a different log, but when you're looking at creating a policy, you'd have this image digest as a policy that you'd expect to see in the log. And so.
Hey, first, yeah, thanks. Useful stuff, cool stuff. It's not clear to me how you're integrating this with the TPM in a useful way. So if I have, well, you're sending all the measurements into PCR11, the PCRs that you're going to get are going to be dependent on the containers that you load. So if you load different containers or load containers in a different order, then that's not going to be able to be used for like sealing values to those PCRs. And also, if you do remote attestation, then you're going to get different PCR values. And so you're going to have to then have some combinatorial explosion of allowable hashes based on the order in which the allowed containers are loaded, not just the individual container that's loaded. And then if you're just going to do this, Like that, so then why it's unclear why bother? And then so if you're going to just then root it in IMA, then you're already trusting that layer, and then you could just report it from that layer. So then what's the value of doing it to the TPM? So can you clarify what's?
Okay. There were quite a few questions asked, so I'm just going to go with the one I remember first. Okay, so if we're loading all of these containers in different orders, yes, the PCR value at the end is going to be different, but you also have this log of measurements, and these measurements are individual. So you have an entry for each namespace or each container image that's associated with it. Let's pull this back up. Well, I don't have one with multiple here, but you'd have this log of the image at this namespace would be an individual entry in the log. And so if you have a PCR that has multiple containers running at different times, you're going to have individual log entries. So you're still going to be able to replay these hashes and get the value that's in the PCR. When you're looking at a policy engine, you'd want to do looking at, okay, I see this container image in the log. I know that I trust this hash, and I know that this log is trusted because I'm able to replay the PCR and get the value that the log says.
Okay, and so remote verifier would then have to get the entire log and would get a quote from the TPM that says, okay,
Yes.
This is the most recent hash, and then replay it through it, and then have to also trust that all of the containers that were loaded between the start of the log and when that container that I'm interested in the integrity of was loaded, that all of the stuff in between has not compromised on kernel integrity in the meantime? Cool.
Yeah.
Okay, thanks. And then the other thing is with the loading, with eBPF loading not being verifiable, I mean, you're already trusting PCR measurements. Can't you load that in early user space and extend TPR, do a, like measure the BPF programs that are being loaded via user space before you reach attacker controlled stuff, and so that avoids that gap? Is there a problem with doing that?
Yeah, that's a great question. So the issue is that eBPF programs aren't executed. They're loaded into the kernel for execution. And so you're never going to have an IMA policy that's going to, with how IMA is currently today, you're not going to be able to catch any of those measurements because they're not being executed in the same way that normal files are. They're being loaded into the kernel and executed in the kernel context. And so the gap is that these measurements don't exist. And so that's a place for future work.
Cool, thanks.
Yeah, I don't know a lot of why IMA essentially.
Why IMA? So because we were working with eBPF programs and because we were looking at integrity measurement, extending IMA was the clear way to go. IMA is measuring the applications that are running. It's extending the integrity measurements from boot throughout runtime. And so IMA seems like the clear place to do this. This infrastructure already exists, and it allows for us to have kind of a lightweight solution using eBPF and kernel modules because we're building off of pre-existing architecture.
I mean, what we usually, why, for example, not DM Verity? Okay, then it's image based. I kind of understand this, and I presume you somehow want to catch all unshares and whatever, I guess.
Because we were initially looking at measuring image, like container file integrity, we were looking at extending IMA through adding this namespace support with eBPF, and then just built off that through doing the container image measurement.
Are there any sort of size issues with like IMA being an append-only log?
It would depend on your IMA policy as well as how many containers you're running. The IMA files can get a bit large, but I think there are some patches to deal with that in the future.
Probably scaling will be an issue at some point.
Okay, so you talked about namespace. What type of namespace is involved? I had looked at doing some kernel auditing of namespaces to try and nail down a container. And that proved to be difficult to nail down because definitions of containers varied a lot between different vendors.
Yeah.
And so I eventually abandoned the idea of logging a set of namespace identifiers and moved towards a container identifier in the kernel itself. That work is currently suspended. Well, it's having a nap. It's not done yet. So I guess the question is, which namespace, or is it a collection of namespaces?
We were initially working with C group namespaces, and that's one line of code. So we've kind of been switching back and forth to see the granularity that we can get for these attestations. So I guess the point is that it's configurable. We're still trying to figure out which one we can nail down to get the most granularity for them.
Good luck with that.
Thanks.
Good talk.
Oh, thanks.
So the measurements, the Merkle tree that you showed, is that just of the file contents, or what all goes into like hash A and hash B?
Yeah, it's just of the file contents.
So not X adders or any other?
No.
Okay, that was. And then second, lastly, the ask for them to be distributed. If it were, I mean, that's pretty straightforward. If you're just like stepping through the file system in a predictable way to come up with that Merkle hash, are you asking that maybe something like that would just be included in like the image OCI, like annotation of some kind?
Yeah, exactly. Yes. If we had a hash that was able to be created also from what's visible from the file system, that's what we would need.
Okay. Cool. Then maybe eventually adding more metadata would be neat.
Yeah.
And if it's like knowing whether a file that was hashed is executable or not might be useful to include it.
Well, we have set cache or like,
right.
You know,
Yeah. Yes, it's just like, yeah, I mean, set UID would be good to know. Set cache would be good to know. Yeah. For sure. Anyone else? Okay. Looks like we might be on for stage here, right?
Check 1 2 2 2 2 2 2 2 2. Check 1 2 2 2 1. Check 1 2.
Check.
Yeah, sure.
Chuck, 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 Chuck.
All right, so we're gonna get back to things. The next two talks are gonna be given remotely, even though I'm listed on this one, so if something goes wrong, I can handle that. But it's gonna be given by Alexander remotely. Hopefully everything behaves. The next talk is gonna be given by I think Tom, who's also remote. So we're gonna have a couple of those. All right, can you go, Alex? Your shot is muted, by the way, on the group button thing. There we go.
Can you hear me now?
You're good, Alex?
Okay, let me know when I can start. I can start, yeah? I'm sorry?
You can go ahead, we're good.
Okay, great. So hello, everyone. This talk will be about fuse mount recovery. This topic was raised by me on the previous Linux Plumbers conference, and it was more about Creo side. And idea was to investigate if it's possible to implement this feature in Creo project to be able to checkpoint restore containers with the few daemon inside. Then I started to work on the LXC project and found a pretty close issue with the LXCFS file system, which we use in the LXC project to virtualize some procfs and some specific procfs and sysfs files like load average, CPU info, etc. And the idea was that LXCFS fuse daemon is the single point of failure, usually on the node, because the fuse daemon is the shared sink between a bunch of containers. And if anything goes wrong with the fuse daemon, with LXCFS fuse daemon, it means that all the virtualized files like load average will be broken from that point. And another motivation is that we have a few bunch of different storage solution like CephFS, Fuse, GlusterFS, and others who utilize the Fuse file system to provide the user space with ability to mount these file systems. And for instance, for CephFS, while we have the in-kernel driver for CephFS, you can't use this kernel driver inside the container workloads if you want to mount this Fuse file, this CephFS file system inside the user namespace, because it's forbidden. So you can only mount CephFS on the host and then bind mount and somehow to the container. That's the motivation to use CephFS Fuse, for instance. Our first approach to this problem was posted on the Linux kernel mailing lists as this small patch series. Effectively, it implements two ioctls that allows to reset the internal state of the Fuse mount inside the Linux kernel, and also somehow reinitialize the Fuse connection to make new daemon work. And generally, I have received no objections against the idea, but implementation was criticized because of one weak point in this implementation that I will cover a little bit later. And also thanks to the community, Bernd Schubert, Miklos Zredi, Christian Brauner for reviews and comments on that. So it was really great. Let's just elaborate the idea. If we have the Fuse mount on the node and we use it, and something goes wrong in the Fuse daemon, it eventually crashes. What it means for us? It means that from this point, the Fuse connection will be broken, and all mounts that we have associated with this Fuse connection and this Fuse daemon will be broken and not accessible anymore. First idea that comes into mind from the first attempt to fix this is to hold the Fuse connection file descriptor somewhere in addition to the Fuse daemon, for example, in parent process, Unix socket, to keep the struct file reference counter to be more than 1 all the time, and it makes connection unbreakable in that regard. And then what we can do with this descriptor, when the first Fuse daemon process crashes at some point, we can start a new one, then reuse the old Fuse connection file descriptor in the new daemon, and just everything should continue to work smoothly. This is a naive idea that comes into mind at first. But the problem is that it does not work as expected. So the idea is to introduce ioctl that will allow us to reinitialize things inside the kernel. So we will carefully clean up in kernel state of Fuse connection, but we will keep all the mounts and all the rest stuff in place without bothering. For example, what we can clean up? We can clean up the Fuse connection flags like no open, no flock, and so on, because these Fuse flags can be initialized in the runtime. And also, we need to drop all non-processed Fuse requests. Those are waiting to be processed by the user space daemon, and user space daemon, of course, cannot process them because he's died. And also, we need to send a new Fuse init request to a new user space daemon. So the new user space daemon will just start from scratch, as the mount is the first one, but just reusing all the mount points. And again, do we have any extra problems here? Unfortunately, yes, because if you try to go this way with any solution that's based on libfuse, for simplicity, your new daemon will crash at some point. Why? Because it will receive, if you start to debugging this issue, you will see that your new Fuse daemon gets a Fuse request from the kernel. Usually it will be Fuse open request that refers the inode number, which is not known for the user space daemon. And I'm sorry, can you hear me?
Alex, we can't hear you anymore.
Okay, I'm sorry. I'm sorry, yeah. The problem is that the new user space daemon will continue to receive, for example, fuse open requests, which will refer the inode number that will be not known for a new daemon, of course, because this inode number is from the old one session. So at this point, we will get an assertion from inside the internals of libfuse, and everything will be crashed. And another question is what we can do with the file descriptors that were opened before a new daemon was started. So it means that we need some way to invalidate all the old stuff and replace it with a new one. And here we can talk about entry revalidation mechanism. The entry revalidation mechanism is is used widely by the file systems like Fuse. We have the entry derevalidate callback for the entry that called after in the first pass of lookup, VFS lookup machinery, if this entry was to let the file system internals to tell the VFS API, VFS machinery to know if this entry is valid or not. And Fuse file system, of course, also implements this callback. And idea was to extend the implementation of this algorithm inside Fuse to make it aware of the effectively connection generation thing. So this is a new concept that we're introducing in this patch set. That the idea is that when you mount the file system at the first time, connection generation is, let's say, 1. But when you call the Fuse ioctl reinit thing, the connection generation will be bigger in step 1. And all the inodes and files and all the stuff that depends on the connection will keep the same connection generation that it was before. And it means that when we enter to the entry revalidation function, we will easily understand if this entry is actual or not. And if it's not, then this entry will be reported as a stale to the VFS machinery in the kernel. VFS will release this entry, go to a slow lookup path, and force a new entry allocation, and then a new inode allocation and look up for it. So we will in this case, we will end up with the new Fuse lookup request at first, and then Fuse open request. While before that change, if you try to open path which was cached before in the entry cache, only the Fuse open request will be sent to the user space, and it will break your user space daemon because the Fuse open request contains the inode number that only known for the user space. And that's a problem. And we solve this problem by doing that. Okay. And unfortunately, that's not all. Because the entry revalidation solves the problem of new daemon crashing, but the problem is that we may have and we may use a bind mounts for Fuse mount. And this problem was originally discovered by Stefan when we have been playing with that proof of concept. And the problem is that if you have the Fuse mount superblock, and if you have a bunch of bind mounts of it, non-root bind mounts, which means that these bind mounts created not from the mount root, but instead of from some subdirectory of the mount, of some file from the mount, you're in trouble in this case, because each VFS mount in kernel refers through the field called mnt root to the entry of this particular mount. and bind mounts are not exclusion of this from this rule, of course. And as the entry becomes stale and invalid, once you try to touch this bind mount, you will fail. And what we can do with that? The idea was, and this is the weakest point of the whole idea, is to introduce another one IOC tool called FuseDev IOC bind mount revalidate, which takes a list of mounts for the Fuse superblock, traverses this list of mounts, calculate as a string, calculate the entry path for each mount root, for each bind mount, then use VFS path lookup, internal kernel API that allows you to look up a entry for some path. And then update the mount root with a new entry. So in the final of this algorithm, you will get the same entry from the logical point of view, from the user's perspective, but in fact, it will be another entry with new generation, and everything will work smoothly. But this approach feels too hacky, and Christian, of course, was not happy about that, and we decided to stop at this point and try to think more. Maybe you have another ideas, and currently we get stuck on that because I have seen that since last 6 months a new feature was introduced into the VFS called move mount beneath, which can be useful in this case, I guess, but I have not played with it a lot yet, and so this is on my plan. And if it works, then we can get rid of this hacky machinery for the bind mount revalidation that is shown here, and we can post a new version of kernel series. The purpose of this talk was to share with you these problems that we come through along the way, and I would like to get any feedback from you if this idea is good or not, if it's useful or not. So it's more about discussing things, not sharing that everything was done perfectly and everything works.
I'm not an expert in Fuse at all, but the situation you're looking at here, as far as the daemon crashing and coming back, is, if you think about Fuse in a lot, in some ways, right? It's a lot like a network file system, right? It's just that the server is a process running on your box, right? And this is very much analogous to the situation that you have when an NFS server crashes, right? And really what you want to be doing, probably, or looking at doing, is some sort of state recovery. I don't know that you'd be able to do that trivially, with existing Fuse daemons, but extending the Fuse protocol to allow for the recovery of state might be the approach you want to take here. And it's probably a lot bigger engineering effort than what you're looking at here, but I don't see a way around doing that, because even if you fix this problem with you get derevalidate working and you are able to invalidate your entries, you still have the problem of open files. Like, what are you going to do with all the files that you have open that crashed when the daemon crashed? And the only way to do that is to recover the state behind the scenes and hook it up to the existing file descriptors.
Yeah, that's
what do you do with the open files? The reason why we didn't care is because for us, the main where we came up with this thing was LexCFS, which is kind of layer on top of proc. And for those files, we're like, well, if we just fail with input-output error, it's fine. Because there are tiny files, people will just read them again. Like, we just got unlucky, we're at the wrong time, whatever. So that's fine in that case. It's a much bigger problem with more different files, different types of Fuse file systems where people actually interact with the file over a long time, as you do with normal file system. The bind mount issue obviously came out of, we need to bind mount this thing on top of the files in the containers. We can't pass the entire file system, so we're like, oh crap, this is not gonna work. Because we ended up having bind mounts to something that doesn't exist anymore. Getting more state is kind of interesting. I mean,
the thing is that the bind mount recovery, in my opinion, will not work. I mean, and if it's going to be made to work, it will be so ugly that we don't want to merge it.
Well, I mean, it can work if you have a way to persist the libfuse state. At that point, when you do get the query for that that inode that is allocated back then, you know what it is and you can move on.
You can't. My point is, you can't update mount root, for example.
Right.
That's,
yeah. So that part is definitely the ugly part, and why we're like, that's what Alex was saying. Like, this doesn't seem like it's gonna go anywhere with that option. The other option, which was like try to get more state during the crash so that we can better recover the server side. That would be effectively if we can keep track. Like if you can recover the mapping from libfuse of like the inode numbers to what actually is, then you don't have the problem because then the number never changed. So you can just reconnect and all of those mine mounts are still valid. That would be the alternative there. The problem is like, how do you capture that thing? You don't want to keep writing it. Obviously, that seems like a bit of a problem. Can you put enough stuff doing like on a codem handler, for example, to pull that stuff out at that time? That's where it gets kind of tricky.
Maybe I don't quite understand the problem you're solving with this bind mount switching. Is the problem that the inode is going, or the Dentry and inode are going to be different when you remount? And okay, and you lose the. Yeah. Okay. Fair enough. Got it.
Yeah, that's the only issue. Effectively, we've got bind mounts to nowhere, and that's a problem. But if we can make them point to somewhere that exists by not having, like, by actually knowing what the old inode is supposed to point to, then that problem doesn't exist. But it would need some way to keep track of that libfuse internal state effectively, so it could be restored.
Yeah. I mean, I really think that probably you want to look hard at NFS and how it does state recovery, particularly in V4. And I think with that, you probably could get something that approaches more seamless recovery. And you wouldn't need to do this bind mounting stuff, right? Because your stuff, presumably the entries and inodes would just still be around.
Yeah, thanks a lot.
Sorry, what?
Thanks a lot for the question. And
okay, sorry.
Yeah.
Yeah.
Do we have anything else? We still have about 10 minutes to go, but we can have a break otherwise. It's definitely gonna, maybe have an interest.
Yeah, I can add some stuff then. It was said that we need to take a look on the network file systems, and I actually did before, and I have seen some kind of very similar machinery in CFFS, I believe, which is Samba-like thing, and they have the file revalidation after connection loss or something, and the idea is pretty similar. They calculate as a string, they recalculate the full path to the file, and then issue the request that will effectively look up the same new entry for the same path, and then replace it, like hotly replace it for the struct file. And yeah, probably we can do something like that, but I have not. But yeah, Stefan mentioned, we haven't played with this one thing because it was not very critical for the LXCFS, and we stopped on the bind bound stuff. And yeah, but yeah, definitely looking closer on the. Sorry?
There's been some discussion on allowing essentially BPF programs to be attached to Fuse and redirect like from one inode to the other and kind of stuff like that. And I wonder actually if you implemented LXCFS in eBPF, that this whole recovery thing would sort of be trivial.
Or having BPF just be the black box. You could have BPF keep track of the inodes and what it is, so that if it recovers, then it has like a BPF map or something it can just use to remap the old stuff to the new stuff.
Sure, I mean,
I don't really.
It doesn't really matter.
Use more BPF.
I mean, for LexCFS, it really doesn't matter. It really doesn't matter, right? It doesn't matter insofar as you only run LexCFS on the host, and you need to start it as a privileged process. It's not like you actually need to use BPF in containers or anything.
Right.
So
yeah, exactly. Yeah, I mean, BPF. Yeah, even with nested containers, we just pass it through. We just bind mount it
Yes.
all the way through. We don't run other instances. So that's not. I don't have a problem with like, oh yeah, BPF is a problem because we can't load it from unprivileged containers. Like, that's not an issue here. And it would be interesting to see like running the whole thing in the BPF might be kind of tricky because of a lot of the weirdness we need to do in like CFS. But maybe having it handle that inode tracking might be an option, maybe. That would be interesting. The other thing I was thinking was like, we could maybe like have a big MFD thing we use and just use that to keep track of that part of the state of LibView, so that if the process goes away, we can just recover that part, and we don't need to actually process it on disk or anything. It's a bit annoying. Like at the same time, the good thing with LexCFS is that we've got very few files and very few things open at any one time. So if we're just looking at this particular use case, that's fine. For other more complex fused file systems, that could be a bit more of a problem. But as we're effectively talking about moving that solution from being a generic infrastructure in the kernel for all fused things to like a per file system thing anyways, then that opens more doors.
Namespace proc. I mean, more than it is now. I'm really joking.
Yeah. I mean, there's a reason why LexCFS exists. We tried that before. No, it's also getting kind of interesting. Like, I don't know, we're putting to think about like LexCFS in general and what it does, because we're now getting into that weird mix where like in some of the container managers, it's a mix of LexCFS and also system call interception and also other things to try and plug all of those things at the same time. Anyway, I think that gives us some ideas. All right, well, we're gonna have like a 5 minutes break to switch to the other speakers who are also gonna be online. And then we wrap up with an in-person talk to wrap up the day. Thanks, Alex.
Huh? How are you? What? How are you?
Good. How are you? You live around here?
Raleigh, 3 hours, 2.5 hours away.
Ah, so you drove down.
Okay, Tom, I loaded your slides and I made you a presenter. Can you just try your microphone, make sure that this works?
Awesome. Yeah, I can hear you. Can you hear me just fine?
Not getting sound, but could just be in the in-room stuff.
I can adjust my microphone volume up if you wish.
We're not getting any sound here.
I mean, we walked around yesterday.
Let's see.
What did you get on yesterday?
Saturday.
Can you try again?
A little bit of
Yeah, how do I sound now?
Oh, there we go. Yeah, we got.
Oh, awesome. Kamalesh, you
All right.
test your
Well, yeah, we've got another 4 minutes, but yeah, it looks like we're good. We've got the slides up and we can hear you.
Okay.
And then I head to the airport at like 1 Saturday.
That's the crazy life.
Yes.
Why are we EBPing absolutely everything?
I was about to make a joke, like, put a bird on it, put some EBPF on it. You know, this would be better.
Get out of jail free card.
It's like everybody. I think the rule is everyone pretends to hate eBPF until someone wants to merge something in your subsystem that you really don't like. Then eBPF is always.
I mean, that's what, like,
Posted to the other mailing list.
For the IMAN stuff, I was like, well, that's a neat one to not do IMAN namespacing.
I have a dumb question. I have been not really paying attention, but like, why not try namespacing propagation?
We can try. I mean, we could try again, but usually the big pushback has been not wanting proc to be tied to like this to limit in C groups. To actually have like, and it gets a bit weird for files like CPU info, like but like massive text files. Like how do you actually
filter that stuff. It looks a bit messy.
Yeah, there was these patches from the SiteGround guys. You probably still remember. They had a patch set to namespace proc, and they made like CPU info and that kind of stuff. Namespace test to the C group file system, and it actually wasn't that massive.
It's not that big. Yeah.
I think
because we struggle with this problem a lot, and this is what I was talking about with resource and resurrecting that. What if we just taught everybody like here's how you actually figure this out?
Well, and it's fine. And the other reason for like not trying to just fix proc is because it's more than just proc.
Yeah, totally.
That's the main right.
Because I can rattle off like at least 6 examples.
Yeah, and that's why like lib resource is maybe a better way to handle that from a user space point of view, instead of being like having to like figure out sysinfo, proc, sys, like all of the 50 different ways to get the same information out.
Isn't this also the case? I thought I don't want to say BPF, but BPF isn't there some, yes, but isn't there some way, or wasn't there some way that you can have a BPF program that sort of is used to virtualize? Oh no, I never remember what they wanted to do. That was LSFMN 2 years ago. So what they did was make it possible to create, you can currently create files in BPFFS, right? And have a BPF program that is responsible for generating info in this file. And what they wanted to do is enable overlayFS and BPFFS and procfs, sort of that you have a BPFS file that you show in proc so that people can also extend it. Essentially. And the problem with this is that it's probably going to be a massive amount of work, because then like proc is all kinds of special work. Just
and people use systems.
Yeah.
I mean, like,
I mean, we've seen that, like, I think it's on Alpine, where like they're using Linux, whatever, like the free command and all that stuff. They all use sysinfo, they don't use proc.
Yeah. I mean,
so it's like, it's the one distro where like you put a memory limit in your C group, you do free in there, and it shows you the host value.
Yeah.
Like, it's fine, we do have interception for sysinfo in Inca, so it's fine, we can work around it, but yeah, like you've got distros doing that, and you've got random software doing that.
Yeah. So that's what, like, what if we start a propaganda campaign or some new like lib resource that is fancy?
Yeah,
as created a new thing and a very long tail of the other.
Well, as we were saying yesterday,
totally.
as we were saying yesterday, like, I mean, LibResource has been around for a little while now. It's mostly Oracle kind of sponsor working on that for the VM and all that stuff. Speaking of.
Yeah, I mean,
it's good. Yeah. But it's like, to get adoption for it, we're looking at like, 5, 6, 10 years for enough of user space to have moved.
Everything that you're doing already doesn't go.
It's 2023, and we're still having a talk about C group V2.
Like, if we ever want to delete all these hacks and like not have to worry about this exact problem, like the thing to start now is right?
Somebody also proposed.
All right, it's going to be time to resume, and we're going to have another remote talk from Tom on C groups. We should be all set, so take it away. You're currently muted, by the way. Just need to unmute your mic.
Just checking out my audio. Is it audible there?
Yeah, we can hear you. Well, someone needs to boost the speaker a bit.
So welcome to our talk of on C group and enterprise user. I'm Kamlesh, and my co-presenter Tom. We both work at Oracle's Linux development team, and we also extensively contribute to the libc group project. So Tom is also Tom is also maintainer of libc group as well as libsipcom projects. So moving on to the next slide, this is our regular safe harbor slide. I'll just leave it there for a few seconds for you to read it. Moving on, let's dive into the timelines of a C group support in Linux kernel, along with the year in which V2 version of the controllers were merged. If you see, V3.16 was the first release which had support for V2 controllers, but it was labeled X because the user had to pass a special mount option when they were mounting the hierarchy, which I mentioned in the bottom of the slide. So if you see, moving a little forward with 4.15, it was labeled stable because you don't need it anymore, the special mount flag anymore. But the same controllers, the memory I/O and the pitch controller were the only controllers available in 4.5 also. Fast forwarding like 4 years or something, 5.2 had more or less all the needed controllers, or I would say the parity, good parity amount, good parity of controllers which are available with 5.12, and I would consider that to be a stable release from a container or an enterprise class point of view. The major one was like, if I'm right, it would be like 4.15, which added the device controller, and with 5.2 we had the freezer support. So moving on to the next slide. You would see that this slide is nothing but it's an compressed timeline from the previous slide with the major milestone along with the enterprise classes picking up the C group V2 support. So the regular question which gets asked is why are the distributions too slow while picking up the C group support like any other feature. But I would say that it was the right thing to do, because with 5.13 is where more or less parity of C group controllers were available, and the moment freezer support was in, it just got picked in by the distros as such. And from now on, I would just say distribution. When I say distributions, distros, I mean the enterprise class distros. So understand that every distro, or every major release is going to be get supported for 10 years or all, which would mean that the distros would be very picky in choosing the stable kernel which they want to use for the major release. Majorly because of making sure that they don't break the KABI often, and they have to consider the bug fixing which comes from upstream, as well as the security fixes and other features which get introduced in the kernel throughout the lifetime of, like, say, 10 years. And I would say that by 5.13 or something, V2 had spent a lot of time building next door in the community distro, so most of the issues were ironed out. Now, if you see, when I speak about enterprise customers here, I'm referring to enterprises which are developing application based on C groups as such. They do have they too are too picky on choosing the distros where they would start, or the feature they would start supporting C group V2 for the similar reasons as, like, long-term application support, which would even run in like many years, like, say, example, 10 years or something like that. And the combinations of releases and the distros, they need to certify. That's we'll discuss about it in more in the upcoming slide. So moving on to the next slide. More timelines. We just love timelines. So in this, we are going to focus more on the libc group releases. For people who don't know libc group, it was the earliest library which was available for applications to programmatically work on C group interfaces, as well as it provided CLI tools which you could use to manipulate. For example, with C group V1, if you want to create a particular C group across all the controller hierarchy, you have you can just use CG create and pass the controller names, and it just gets created in one command line. So if you read it from left to right, you would see that libc group was released with C group V1 support even before the distros picked it up, and down the line, C group V2 support came after the C group V2 support was picked up with the distro. And after that, we have interesting features like abstraction layer and systemd support, which we would speak in the upcoming slides. Can you please go to the next slide? Before we dive into when and where you can use libc group, I would say that libc group currently supports V1, V2, and the hybrid mode, where you can have V1 controllers and V2 controllers mounted at the same time. That means that you can use the same function call or the same tools to just work on all of these setup modes without needing to worry about passing any flags or special things which is needed. So this is just a very minimalistic list of places where libc group can help applications and users. As we spoke, programmatically, you can manage the systemd scope. This is very important for applications. Those who want to manage their own substrate, as shown in the figure in the right side, the topmost figure, where you can see that in the one major thing is like pacing of tasks. Systemd would just take care of placing the task in the right C group, which you don't want to happen. And another interesting thing would be like you can just use the known interfaces to read or write the controller settings, and you don't need to learn new syntaxes. And all the tools which are available now are well aware of handling both systemd versus the delegated and the non-delegated interfaces. And the biggest strength has been it can allow you to manage and create complex hierarchies in terms of multi-level nested groups or managing hundreds of hierarchy which are mounted. And it supports threaded controllers, which means that it understands threaded mode completely, and it understands systemd transcendent mode. It allows you to read and write every controller settings. I guess systemd doesn't allow you CPU set. And we have introduced Python bindings, which would mean that you can just say import libc group and just start scripting, working with C group interface as such. Moving on to the next slide. This is just an slide on what was the contribution and how it went. So in 2008, we started up with V1 support. And I guess it was back then it was the only library with it was available for programmatically working with C groups as such, and it was available in most of the distros. I guess when C group V2 was announced, the distros had some other plan, and there was a dip in the development phase. In 2019, Oracle picked it up, and ever since we have been maintaining the library, and we have contributed to features like support for C group V2 hybrid mode and other cool features like abstraction layer. Abstraction layer would allow allow you to move from V2 C group V1 systems to C group V2 system without like any effort, and systemd again in Python binding. And I'll take this opportunity to thank everyone who contributed to libc group, and would ask all the distro maintainers or the package maintainers to pick up the latest available libc group. Let's move to the next slide. So let's take an example of how the applications or enterprise application would generally support C group as such. So if you see, let's take an application A, which is in nature it's just a CPU intensive workload, and it's again going to get supported for a long time. So let's say application A picks up support for V1 when it's available in the distro, and it starts using C groups for grouping the tasks and allocating the CPU shares based on the nature of those tasks. And once the same CPU controller is available in V2 also, then it starts supporting V1 and V2 interfaces. And similarly, when it's available for V2 only, when the distros pick up V2 only, then it just starts drops the support for V1. This would be a very ideal case, but that's not how the real world works. So, can you please go to the next slide? In real life, if you see, an application A could have just done a release X, and C group V1 just got release X, and it would just support for 10 years or odd. And C group V1 could have just got picked up in the distros, and the application A would start supporting C group V1, which would mean that it needs to support two different modes. One is no C group and C group V1. Probably it would be including a lot of ifdefs. And just before the end of life of the version X, there would be another release, say X+1, which gets released. Here, it needs to support C group V1, and again, non-C group option. And again, in its own lifetime, like in its own lifetime, it would see that there's support for C group hybrid mode as well as C group V2. And again, it needs to support both of them. And again, we would have another release which would just get done before end of life of X1 as such. And similarly, you would just use the C group hybrid mode, C group unified mode, and drop the support for none. So if you see the common pattern across all this thing, is like the major burden is not about the adoption of C group as such, but maintaining the different versions of C group within an application. Think of a controller which is available in V2 and which might not be really available in V2 in the same form, or think of the control interfaces which changes with every kernel. So that would mean an application needs to be like supporting different versions of distros, different kernel versions with different controller options available, and we are not even considering the other Uber features or other non-C group related features the application need to support. And the major thing is we don't know when the new feature when the application starts using the new feature, we don't know how the customers are going to set up the C groups. It's just an assumption which might break as well. Moving on to the next slide, let's remove all this extra details and just let's focus on what let's make it too simple, right? So that is an enterprise class distro which would pick up kernel features, and there will be services and packages which work around C groups which will get updated. That would mean the application needs to support it. And the question which people ask is why are the distros not picking up the greatest available is like it takes few years for stabilizing the application over the years, and no distro is going to just throw it away as such when it's working and reliable. So Tom, I'll just pass it over to you to speak the other technical challenges as well as the solutions which we provide from LPC Group. Thanks.
Sure. Thanks, Kamlesh. So thanks for laying the background there. Oracle's obviously well known for databases, clouds. In fact, I just heard today Oracle has something like 10,000 products, but this isn't a talk about Oracle products. It's more of a focus on enterprise users and how the challenges they're facing as they try to migrate to the latest and greatest. On top of that, Oracle obviously also maintains a distro. So we have thousands and thousands of users all across the planet running whatever applications are running. Some are brand new and some are written well, following the latest and greatest guidelines. But some have been around for years or even decades and predate C groups, predate systemd. And so they have a lot of legacy background. And so how do we help them move forward and migrate onto these new features? Before I dive into these use cases, again, like Kamlesh said, I like to thank everybody for their hard work. This definitely is not an indictment against C groups. This isn't an indictment against the latest and greatest. In fact, we love it. It's just sometimes difficult for us to help our customers navigate there. So I've got 4 examples in front of us that we've seen come up over the last few years with our our enterprise customers, and these would be, spoiler alert, these would be great possible discussion points at the end. So the first one, I'll start in the top left. So say you're an application and you've been running on C Group v1 this whole time. Your goal is to dedicate 70, 80% of the CPU to your app, whatever it may be. And so one way that we've seen a user go about it is they've said, hey, let's set up exclusive CPU sets. On v1, the root C group ignores that. On v2, it behaves perfectly, which is awesome, and it does obey it. So if you set up a child or oracle.slice and you gave an exclusive CPU set, the root would obey it. So that's one snag we've seen, which obviously you can case statement, you can if that, but it's been suboptimal for users. Moving down to the bottom left then. So UEK7, which is our latest released kernel, that's based on 5.15 upstream kernel. In that particular release, a parent C group, again, so this would be on a C group v2 system as well. A parent C group, so say you made a C group, oracle.slice, it is required to keep at least one CPU available to itself, even if it creates exclusive CPU sets below it. So if you made 2 child C groups, database.scope and cloud.scope, they wouldn't be able to use the entire CPU set that's been allocated to them. In other words, again, one would have to be dedicated to the parent, even though the parent can have no processes in it due to the no inter-process node rule. This has obviously been fixed on 6.6 and probably was fixed somewhere in between, I don't know where. So our newest Oracle release, when we have a new kernel come out, it'll have it. But this will be something that our internal users and our distro users will have to live with for the next, we've got 8 years left of this. So yet another potential. Yeah, I saw the hand pump there, Christian. So yes, this will be a recurring theme. So I'd love to hear thoughts on this one as well. Moving to the top right, So depending upon which kernel you're running, depending upon how your systemd is configured, and depending upon what your applications are doing, processes will show up in the root C group. But a process in the root C group has roughly the same amount of CPU.shares as system.slice or machine.slice. And we have seen users get into the case where either due to poor configuration or bad luck or straight up nefarious applications. An example of that would be the application expects real time. And depending upon the distro and its various release, some of them didn't. It's hard to get real time enabled in a child C group due to the config RT group sched config setting. They just move their process to the root. If these processes start hogging CPU, suddenly you get things getting starved. So that's been another challenge for some of our users. Finally, moving to the bottom right, then the single writer rule, and this kind of relates then to some of the previous ones. So, in a nutshell, the single writer rule says that a single entity, C or systemd, owns the hierarchy, which is a wonderfully simplifying requirement. I love it. But again, many of these products predate it. And so they expect the ability to write up and down the C group hierarchy. So the official mechanism to work around that is a delegated C group. Again, company.slice/database.scope or whatever. But going back to like the bottom left example, then suddenly that means depending on which kernel you're running on, you might have wasted CPUs because you've had to reserve them for a parent C group that can't have processes within it. I think this is a good rule. I'm glad it was adopted, but again, the people that existed prior to this are struggling with it. So life's not all bleak for us. We have come up with some solutions over the last few years that have helped several cases, but I brought up those CPU ones because I think those are discussion points we'd like to talk about. So here are some we've come up with in the past, and I know, so for example, top left, we talked about this at previous LPCs. We now have an abstraction layer. It's released in libc group. So if a customer wants to talk CPU.shares, they can. We'll convert it to CPU.weight or whatever setting, which is readily mappable. We can do that for them. There are some more challenging settings that we don't map, but at this point, no enterprise user has requested them. So if that is a request upstream, just let us know and we can definitely get them in there. In addition to, so the abstraction layer is available CLI, C, direct C APIs, Python APIs, and as highlighted in the top right, also via cgconfig. Cgconfig is kind of an interesting thing. So that, again, is a feature where, given a configuration file like the example shown there, a user can have C groups be created at boot time or at basically when cgconfig runs. So you could, obviously restart it and make it happen then. This previously would conflict with systemd owning the entire hierarchy, but now, I noticed we have a little typo here. We don't have different, anyway. We can create a C group hierarchy that obeys the single writer rule. So in other words, we'll have it delegated properly. So this has allowed many of our customers to migrate from V1 to V2 fairly seamlessly and obeying a reasonable amount of rules. Not perfectly so, but also not hampering their development either. And so finally, then bottom left, as I was hinting at, we added systemd delegation support again via CLI, C code, Python, and cgconfig. So a user can, with a single CLI command or basically 2 lines of C code, create a delegated C group. Of course, they could use dbus too if they want, but as you all know, that's rather complex. So those are some of the solutions we have. But I guess that what we're looking for is ways we can continue. And I heard you, Christian, before the talk started, another C group V2 talk. Based on Kamalesh's timeline, we probably are going to be having these discussions at least within enterprise world for another 5 to 8 years, as we continue to migrate customers and apps and our distro from V1 to V2. So questions for you, like, are there upcoming features that are going to continue to break our enterprise users? So again, like the no process and internode rule, I love. but it's broken them in the past. The single writer rule I love, but it's broken them. Otherwise, other new features that'll also help them. And I guess then questions too we would have are, what other mechanisms and tools do we have to help these users migrate, especially when they have to run on old distros that don't have the latest greatest systemd or latest greatest kernel features? What options do they have available to them? So thank you. Open for questions here.
Yeah, I was just gonna make a comment on the systemd version stuff. I don't remember if you touched on it earlier, but we're definitely in an interesting spot now where for a while, especially with containers, if someone wanted to run like an older distro, and I think CentOS 7 was kind of the most common for that, the solution tended to be, well, you're booting a system that's on cgroup 2 right now. If you try to run that distro, it's gonna blow up because systemd from CentOS 7 is not super aware of cgroup 2. So you just reboot the whole system, set unified hierarchy to 0. Yay, you've got cgroup 1 on the host, things work. Now the point is that we've got the opposite issue that's coming up now with distros, where it's the opposite. What's going on? Okay, so it's the slide. Oh, okay. Yeah, sure. We've got the camera here and we've got this one there. Okay, there we go. So yeah, I was going to this also one there. Okay, yeah, so that's a bit of an issue now with the latest systemd having removed cgroup 1 support. Okay, well, some distros are shipping some snapshots at this point because we've got images that don't boot anymore. So when that happens, you're effectively like, well, you have to choose now. Do you want this host to be able to run old stuff or to run new stuff? If you want both on the same machine, you can't. So it's starting to happen. It's not surprising. I mean, we've had those chats with Leonard for a while, and like he wanted to get rid of the cgroup 1 support like multiple years ago. So it's just starting to happen now, and it's something to keep in mind because you're not going to be necessarily able to mix and match containers on those systems.
Scheduled for removal next year, I think. And I'm supposed to ask, library support for transient units, it's something that could be interesting in having in libsystemd itself, and whether you'd be up for contributing this.
We would definitely be interested in helping with that, yes. Again, the snag for us is by maintaining more features in something like libcgroup, it's easier to get these changes back into our 5.15 kernel, our older kernels than that. When we do systemd, obviously it being, I'm not gonna use the word monolithic, but much larger, it's much more challenging to get latest and greatest systemd features backward into older kernels. So, but yes, we are definitely interested in participating there.
I have one question. So the libcgroup, are you supporting cgroup v2 isolated partitions? CPU set isolated?
Kamalesh, I don't recall right offhand to you.
So it's going to allow you to do anything and everything which you just do it within the command line, right? If you're going to say you're going to pass on any controller setting for cgroup CPU set as such, you can just do it here. We're not providing any policies here. We're just helping you programmatically just do it. That's it. So
is there
if
anything
you write
special
a
that
particular CPU set and
Yeah, instead of root, you write isolated. And
yeah,
oh sure,
then,
yeah, you can
do
you
those.
can 100%
You can
do
do
that.
those. We don't give any
The-
policies or restrictions as such.
So I can just, so you don't, I can write any string to the
Yes.
intro.
I mean, which is legal. I mean, we don't check it. I mean, if the kernel is going to throw you error, we're going to return that error to you.
Sorry, if anybody else has question. So the other question, systemd v2 support, right? You have root cgroup. Currently, you can send a dbus message to systemd, and root cgroup can, change CPU set. The same thing with isolated. There is no way to say systemd, CPU set isolate these CPUs instead of just regular CPU set. So is it systemd is planning to do it, or it's waiting for contribution from someone?
I can't speak for systemd lately, but I recall a discussion from years back, and they had no plans to support CPU sets, period. I don't know if their mindset has changed since then, but They had a design
They-
methodology that didn't match it. So
They do support CPU sets. They didn't support it in C Group V1 because the controller was considered broken, but with C Group V2, they do CPU sets, like full-blown CPU set support.
Oh, awesome. I'm glad to hear that because as you can tell, we're still living in enterprise world and we're still V1. So that's good to know. Thank you.
For C Group V2, there are some old C Group V1 features that are not in C Group V2. Is there anyone in particular that are needed but are still not in C Group V2 yet? So what do you think?
So
Any
C Group V1
example
features, are you asking for C Group
Yeah.
V1 features that aren't in V2?
But not in
Yeah,
V2.
there's many. So like one of them that I can think of a while back that bit an enterprise customer of ours, they had decided that sched domain relax level or some whatever it's named, I don't remember its exact name. So CPU set.sched relax domain level or something was really helping them get better performance. There is no equivalent feature in V2, and I sincerely hope there never is. So that would be one like in libc group. We'll let you set it if you're on a V1 system, and on a V2 system, depending upon how you've asked us to configure it, we'll either throw an error or we'll silently ignore it, depending on what your request is.
Okay. I think it can be implemented in V2 in some way, I guess. But the sched relax domain level only apply to the whole scheduling domain. So you need to apply on in terms of C Group V2 is on the partition level. So you have one partition is one scheduling domain. So you can set relax sched relax domain level for the whole partition, I guess. So it can be implemented.
That would be interesting.
But,
we have a couple customers that would be, I won't say I love carrying that idea along, but they would definitely be interested in it. So yeah, if you have ideas, we'd gladly listen in on that. That's one of the sticking points we've had in the past.
Okay, yeah, I certainly believe that it can be implemented in C Group V2 as an extension to the partition interface.
Awesome. Yeah, thank you.
Yep.
And I mean, there's definitely still some gaps. I think the most recent we kind of had to deal with on our side was it net prior or net CLS? Like one of those was kind of weird. You can do it some other ways. I think we ended up doing it through NFT, so using the NF tables features to effectively get the same result, and that worked. I guess one question for the libc group stuff is, when you're supporting both transitioning from V1 to V2, did you look at effectively converting the devices policies over to BPF automatically so that someone could just have that work? We've effectively done that in libelxc, where someone can set the normal text version of a devices C group allow list, and that just turns into the new magic eBPF thing that you need to load.
Oh, nice. I didn't realize.
The question says it was a pain to write.
I was say we have finite bandwidth of engineering hours, but that sounds very appealing. I will admit I will go look at your LXC implementation. I'm intrigued by that.
Yeah, so you can probably look at the code in libelxc, because that's effectively what we had, where like people were doing like lxc.cgroup.devices.allow or whatever, and you can just replace that. The cgroup 2 version looks identical to in as far as the config file is concerned, but turns into BPF instead.
Oh, awesome!
I don't know if you want to add something.
That's good to know. Thank you.
Yeah, I mean, I'm just rehashing what we said years and years ago. So it's at some point it becomes becoming a, I don't know, radio, whatever you want to call it. But yeah, the original idea had been that we sort of have a mock C group file system that internally translates C group V1 write requests to C group V2 and possibly the other way around. But I think there would be a massive amount of work, and it doesn't really. Yeah, it doesn't really work nicely. Like for the devices controller, it kind of works because we have a separate abstraction layer. So for a container engine that, for example, configures these are the device settings that I want to apply, then you can parse them, and then you can transparently translate them into an eBPF program, but it obviously doesn't work for direct consumers. So meaning if you have some sort of program in a container that expects to write a devices program through this C group file system directly through the devices controller, that simply doesn't work because it doesn't exist anymore, right? There is no devices controller. That's a BPF program, so there is no file to write to. So these applications you can't really salvage.
Gotcha. That makes sense.
Any direct consumers, what I'm trying to say is of the C group file system and expecting a specific version. That's just, yeah, I think we're past the point where we can meaningfully support this.
Agreed. Yeah.
It would be interesting to you. Is this like something that you have problems with? Is this something that you do actually support?
We don't currently, I have yet to run into a major problem with devices like that, but I think that would be, it's just a matter of time when somebody finally comes to us with that. So yes, we would be interested in a similar solution to what you've done. And I think we could do a very similar C group FS kind of thing like you did, as long as they're interacting with libc group and not directly with the sysfs.
They're using libc group, which is a library, they get a CG write or something for devices that allow to this value, and they just need to turn that.
Yeah,
so
yeah.
It's the same deal as what we do in libLXC, where like if you do have the BPF program,
Sure.
you just
Yeah, my point is you can't have like for example, we would be a prime example when we would be running inside, somebody would using a distro with a Lexi binary from I don't know what, and we assume that there is C group V1 in there. We would be trying to write directly to the C group file system, and that just wouldn't work because we wouldn't find any.
And we were considering doing stuff in, like with LexiFS, with like a fuse file system that pretends to be V1 and does V2, but that's just just never really got anywhere, and I think it's kind of too late for that at this point. The concepts don't really matter. All right. Do we have any other questions? Yeah, there's one like that.
In one of your slides, you showed an example of etc cgconfig.conf configuring a database.slice. Is that an implementation on top of systemd abstraction, or is it the libcg group you are writing some tools to apply those settings into systemd slices?
We are making direct dbus calls so that it's properly delegated and systemd recognizes it as a delegated C group.
Okay, thank you.
No worries.
All right. Anything else? Nope. I think we're good. All right. Thanks a lot.
Thanks, everyone.
Thank you. And with that, it's the end. No, we still have one. Yeah, we still have one. We still have one in person. In person. We're losing Taiko. Oh, yeah. All right. So let's switch back to in person. You had it, right? So we're going to put this one away. Go. Actually, are you into the VQ button thing?
Yes. I should be able to just see you there. So I'm going to mark you as presenter.
So you're going to get the control. And then here we can pick up your thing, which was this one, right?
Yes.
Okay. We'll pick that up. So you're up. And now you've got the control for the slides right here. So we can go back. Yeah, we're going to go back to the first slide. There we go. Yep, all good. And when you want to share your screen, you should be able to just do it there, and that should work fine. Yeah. Are we on? Okay, we're slightly behind. Cool.
Should I start? Okay, cool. Hello, everyone. My name is Radostin, and I'm a PhD student at the Scientific Computing Research Group in Oxford. Yeah. Yes, I'm a third-year PhD student at the Scientific Computing Research Group, and I've been working with Adrian on introducing encryption for container checkpointing. So over the past few years, container checkpointing has been introduced in several container engines, container runtimes, and more recently with container orchestration systems such as Kubernetes. And it is used with different Linux distributions, and they all have the same problem. When used in production, container checkpoints contain sensitive data, which could be passwords, user data, or essentially application data that is included in the checkpoint. So one example of how encryption is being used to protect this data was presented a few years ago by Andy. Essentially, how they introduced the encryption mechanism in the Borg system is creating a tar archive and then encrypting it and then saving this in external storage. However, there are some problems with this. First, I think enabling this, for example, in Kubernetes and making it available for different distributions is not very easy to maintain and easy to introduce. For example, if we want to introduce this in Kubernetes, we have to change the container runtime, and there are multiple of them. And also, we have to modify the container engine, and key management is also a big problem. How do we distribute keys and then make sure that they're available across different cluster nodes? And the performance, of course, is there is an overhead of encrypting the data itself, but also performance overhead in terms of how much time does it take to encrypt the checkpoint. So in Kubernetes, the checkpointing mechanism works by essentially, for example, CRYO calls runc and runc calls CRYO. CRYO creates a checkpoint, then we save the configuration files and we create the tar archive. So we're looking at how we can introduce a built-in mechanism in CRYO that would allow us to encrypt the checkpoint, the image files themselves. And CRYO already has integration with GNU-TLS, and GNU-TLS provides the encryption primitives that allow us to encrypt essentially the images that CRYO creates. We can reuse most of the code because there are a few functions that read and write images, and we just need to modify these functions to encrypt the data when it's being written and to decrypt it when it's being read back. By encrypting different images, we can also extend the crypt tool, which is a tool that allows you to decode images and modify them. And we can also optimize the way encryption is being implemented, because there are different types of images in CRYO. They have different format, and by essentially encrypting the specific parts, we can choose what ciphers are being used, for example, for encryption. And also by implementing this in CRYO, we can essentially provide end-to-end encryption, meaning that the data is encrypted before it's being written to disk, and then it's decrypted when it's being read back. So this sensitive data is never being stored in plain text. So there are three main types of images: protobuf images, raw images, and memory pages. In CRYO, protobuf images are essentially data structures encoded in protobuf. And for this type of images, we use a stream cipher that allows us to encrypt small messages and use nonce or number used on ones to provide randomness, so that if the same plain text is encrypted multiple times, you get different ciphertext. The implementation is when the implementation software is performant, and it provides authentication, meaning that if the ciphertext is modified, the decryption is going to fail. So this is an example of how the checkpoint restore functionality in CRYO looks like. So we have these PB write and PB read functions, and essentially these functions are used throughout the code base to read and write image files. And then essentially adding the encryption mechanism looks something like this. So we first load a public key. we generate a token. The token is used as for symmetric encryption. We encrypt the token itself and save it into a new image file called crypto.image. We then use the token itself to encrypt the content of the image before it's being written to disk. So essentially, the only image file that is being created that is not encrypted is the new image file that contains the encrypted token. During restore, we first load the private key. The private key is used to decrypt the token. The token is then used to decrypt all other images in Creo. And another image type are raw images. So these are essentially images that are created with external tools such as IP tables, IP, and the way this works in Creo is Creo creates a fork that then runs exec with the external tool and then uses the standard input-output file descriptors to save the data to files. So essentially, to introduce the encryption here, as we can create something like a pipeline. So we fork a separate process and then replace the input-output file descriptors with pipes. So that for example, tar is going to write to a pipe, then the encryption process is going to read from the pipe and then write to encrypt the data and write it to the output file. Then the reverse is essentially during restore. And then for memory pages, this is pretty straightforward because essentially we just have to the encryption is straightforward because we just have to encrypt every block. However, during restore, it's slightly more complicated because we have things like copy and write memory pages, but also functionalities such as pre-copy and how to deduplication. So pre-copy, pre-dump is essentially iterative checkpointing. So it means that we want to be able to decrypt individual memory pages. In contrast to other image files, memory pages have fixed block size. So I reached out to Daki from the GNU-TOS team and asked for essentially advice on how we can implement this to be more efficient. And he suggested to use the AES XTC cipher. So it's essentially, it allows us to use initialization vector instead of nonce. And this means that we can use in-place encryption. So we can encrypt every block. Every memory page has a separate block, and we can also use the hardware acceleration for AES, which is about 5 times faster. And it's a widely used encryption encryption algorithm. So the way this works with standard checkpointing and restoring images is pretty simple. So we generate AES keys, we save them to the image file, and then we just encrypt the data and decrypt it on restore. It becomes more complicated when we have to do the restore within the position-independent code in the parser, in a position-independent code because we cannot use GNU-TOS there. So again, we can use a pipeline. So we request the memory pages that need to be read from, or essentially the offset that needs to be read from the pages images and the number of pages. And then we use the pre-read system call to read this part of the memory pages, and then use process VM write v to essentially write the pages in the correct place after they're being decrypted. So this is essentially the most efficient way I could think of implementing this. And we also extended CRIT to be able to decode encrypted images, and this is pretty straightforward. So when the cipher image, when the image with encrypted keys exists, it means that the checkpoint is encrypted, and it essentially automatically detects that it has to decrypt the images. It also has a TOS key additional option that allows to specify the path to the decryption key. So, for example, we extended the DTM tests. So when we run all create tests, they're running with encryption and without encryption. And we can also specify the private key that is used for the tests. So I will show you a quick demo. So for example, so this is a default configuration file that allows us to specify different key options. And in this case, we have the encrypt option specified. So when this option is used during checkpoint, Creo is going to encrypt the images. So this essentially just creates a checkpoint of the loop process above. And the cipher image essentially contains the keys. So it looks something like this. And if we want to decrypt an image, it essentially loads the key from the cipher image and then decrypts the content of the image itself. Then essentially the restore mechanism works in a similar way. So it automatically detects if the images are encrypted by just checking if this image with the key, with the encryption key is there. And then it loads the private key, decrypts the symmetric key, and then decrypts the rest of the images. One thing that, so for example, we have different types of workloads. Some applications use many threads, meaning that when we create a checkpoint, this checkpoint is going to contain a lot of small files. Other applications, for example, in this case, memhog, they just allocate a huge bulk of memory. In this case, the checkpoint will contain large amount of small amount of files, but very large files, in this case, memory pages. And so for example, this creates a checkpoint for memhog, and we can see that there are different files. We can see that the image is encrypted because it contains this cipher.image. In contrast, if we run something like stress-ng, We get large amount of small files because it creates many threads, and this also. So when we did the evaluation on how this encryption mechanism compared to, for example, using OpenSSL, GNU-TLS, Edge, GNU-PG. So essentially what we did was we used an action script that is triggered with the post dump hook, meaning that after the checkpoint is created, it will turn this script and it would encrypt the images. So when we have large amount of small files, then it takes a lot of time to iterate through the images. But essentially we can see that using in-place encryption or encrypting the images as they're being written is generally faster. And conclusion is we implemented a mechanism to encrypt images within Creo. It allows us to be easily integrated with container engines and container runtimes without needing additional modifications. And it allows us to decode the images. And for future work, we want to integrate this with pre-iterative checkpointing and memory deduplication, and perhaps introduce compression for the images. And thank you for listening. And do you have any questions?
Andre.
Yeah, if we're talking about checkpoint restore containers, we need to think about checkpoint restore file system. So should we encrypt the file system snapshot? And if we should to do this, how we are going to do this, and how it works now in Kubernetes, for example?
So the file system changes are saved. Essentially, they're handled by the container runtime. So Adrian, I think that he implemented this in Podmod first. Essentially, it gets a diff of what files have been changed in the container. Then essentially this diff is saved as a tar file. I mean, this is handled by the container runtime. Essentially, Creo doesn't counter the file system changes. But also, we have to use different encryption algorithms. Like, for example, in this case, we have public-private key. So to create an encrypted checkpoint, we need only the public key itself, meaning that in the case of forensic analysis, for example, when we want to create periodic checkpoints without the need to decrypt them, we want to decrypt them on a specific file system. And with file systems, for example, if we use symmetric keys, the key is within the container or within the system that creates the checkpoint. So yeah, it's more complicated. I mean, we don't currently handle file system changes in Creo, right?
No, we're not going because it's it's not the work what we're supposed to do. We just create the checkpoint restore process, and then other tooling should create a snapshot of file system.
Yeah.
And if we are talking about Kubernetes, it looks reasonable to use the same mechanism to encrypt the file system and to encrypt the set of images, because set of images is it's like the other part of the container.
I mean, so we have two options. One is to encrypt the images as we will do with Creo. The other one is to, for example, encrypt the OCI image that contains the checkpoint. Like we were discussing this, and there are different types of, like for example, if you want to introduce encrypted OCI images, then we have to change different projects, and it will be introduced in a different level.
So could you elaborate a bit more about your memory page protection? So like use case and threat model, because you're only requiring confidentiality for that, you're not requiring integrity. So what are you using it for? Maybe you mentioned, I missed it.
So the idea of using this XTC is to allow us, for example, during memory identification to remove specific memory pages from the checkpoint without essentially while preserving the ability to decrypt the content. Because if we encrypt a continuous bulk of memory and then we delete part of it, then it wouldn't be possible to decrypt it if we use, for example, stream cipher or. Did that answer the question?
Oh, no. You're going into mechanism. I mean, you could do MAC on top of IS60 page. So there are ways to solve it, encrypt it. But what is like? Why did you? So you said that you want to exclude that information from the.
So essentially, and there's something called iterative checkpointing. So the idea is to be able to, and auto-identification. The idea is to use a work cipher that would allow us to use these features.
The question, why encryption at all?
Yeah. So why it's a mechanism, but I'm not understanding what you're using it for.
To protect the content of the images.
The idea is to, if you want to migrate a container and you use a public registry for the.
No, for image encryption, I understand, but I'm not asking about. I'm asking about memory page encryption.
Yeah.
So because he was talking about two different things. So image encryption is clear, why is it?
Okay.
But the memory page encryption is what I'm trying to understand. What is that use case for?
Because that's going to be moved through a public registry to another system to restore.
So
saying that is not saved on the checkpoint. So you wanted to live migration essentially?
Yeah, effectively.
Yeah.
Okay.
So memory pages is essentially this files pages.image.
Okay.
They're part of checkpoint.
But then you need integrity. Because if it's moved through, untrusted party, you need integrity on that memory page.
Yeah, so
you should mark or do something on top of.
You can create a hash of the content. So essentially, how do we ensure that with this string, with this cipher, if you modify the ciphertext and you decrypt it back, you will get something. It means that we have to introduce the authentication mechanism.
Yeah, because IS-XTS doesn't have integrity.
Yeah,
it's only have limited malleability. So.
But we have to introduce this on page by page. So.
Yeah, so it would have to be marking, essentially applying the mark on top of that. Yeah.
Yeah. Thank you.
Anything else? Oh, all right. Thank you very much. And with that, it's exactly 6 p.m. and that's exactly the end of this MicroConf. So thank you very much for coming this year too. I hope to see you all next year again. And I believe there are buses about to take us to wherever we're going to have dinner and drinks. Thank you.
I was just using it. And if you want, I don't think I have to pray.
Okay.
Okay. Well, we'll see here. Hey, everyone. My name's Steven. Thank you all for coming to the Debugging Micro Conference. This is the first time we've ever done this. So really excited to have a full room in here. That's really awesome. Thank you all. And yeah, I don't have too much to say beyond that. This is a little different from, say, the tool chains, which is focusing on debuggers. It's about just kind of the confluence of debuggers, debugging formats, KDump, Kexic, all sorts of things that affect how we try to solve problems in the kernel. So that's what we're here to talk about. And I guess with that, as everybody's getting settled, I'll turn it over to Peter, who's going to be doing our first talk here, the taming of the kernel dump. Thank you.
Hello, everybody. Again, I'm very happy that there is a debugging micro conference for the first time, because I believe if testing is believed to be underrated, debugging is probably even more so. It's not cool to debug, like it's cool to write new code, but not to debug. But I'm really glad it's getting recognized now. And my topic is something that I have been doing for about a decade, I think, but I never was paid for it, so it was always a hobby project. That's why it's moving so slowly. And I'll try to present what it's all about. Good. So how do I move that on? Okay. A bit of the background. Why did I even start this lib kdump file thing? Well, it is a library that allows access to crash dumps, like system crash dumps. And I feel like that wheel was reinvented too many times. So for the first time, it was done in lcrash. Can anyone still remember lcrash? That was a terrible tool. It was written by SGI as part of the LKCD, which was just Linux kernel crash dump project. But it was one of the first of its kind. So, okay, I'm not really ranting, but okay. So they were the first people who had to somehow interpret the data. Then it was implemented in crash again. Then it was implemented again in makedump file, because makedump file can now read an existing kdump and refilter it and save it again as a kdump file. So they also needed some routines to interpret the data. And obviously, they also have to support the ELF format. I'll get to that. And then at some point, I wanted to identify unknown core files that came to SUSE customer care. So like they got a kernel crash dump, but didn't know exactly what kernel version it was taken on. So I was like writing my own tool that was kdump ID. And when I saw that this wheel has been reinvented, I was like, okay, we probably should write a library. So yeah, let's make the wheel. It should be reliable, universal, one wheel to rule them all. Okay, maybe not the last one, but now I wanted to make it good. And now when I was writing this slide, I realized that the goals are probably a bit ambitious. So first is, so I'll spend a bit on these design goals because it can explain why I wrote that library the way I did. So the first thing was I would try to mimic what actual hardware does. So if there is something in the hardware specification, I will preferably use it, at least as a fallback. The reason for that is I don't want to rewrite it again and again and again if the internal representation of the data structures changes in the kernel. And it has proven pretty good. Like these routines have not been touched except when new paging formats were added to the specification itself. So for example, for the IBM mainframe, it has not changed, never ever. Their specification is future-proof. They can do 6-level paging if needed. Okay, theoretically, I don't think they have the hardware for that, but okay. Anyway, second thing was I wanted this to be cross-platform, because occasionally we received dump files from an architecture that was not common. Well, okay, obviously SUSE had all the architectures that they ship, but yes, if you could do something on your desktop, that was easy. If you had to reserve something, sometimes you found out that all the machines were taken, or they were not taken because they were slightly broken. So to install a new operating system on it, you spent like 1 day finding out how to boot it. So I said I didn't want that. I want just you get a crash dump from any architecture, you open it on your machine. I didn't want to make it Linux specific. And in fact, there is already support for one more operating system. You can use a libkdump file to read Zen hypervisor dumps and see the Zen data, not the Linux data, which is in DOM0. You can really also get the hypervisor data. And I wanted to preserve that. A crash can also do this. But I was like trying to do something more generic. So theoretically, if someone wants to adapt it for, say, OpenBSD, well, there is a way. I'm not doing it because I'm not involved in that project, but theoretically it could be done. Like there's an attribute which is a string, so you can just, if you write something that's not supported, you just get a nice error that the operating system is not supported. But yeah, theoretically it's ready for that. Right. Next, it should be small enough for the crash kernel. What I mean is, I wanted, and I probably still want, to replace the implementation in make-dump file. Now, make-dump file runs in the crash kernel reserved area, which means you don't have a lot of memory. So it should be, yeah, like the library should not be resource hungry. Next, that is related, it should be fast enough to run on crashed system. The thing is, when your system crashes and it takes a dump file, that is downtime. Essentially, the main system is not operational. And you want to come back online as soon as possible. So I was really looking like to make all the hot paths fast. And yeah, theoretically, if you replace that in make dump file, it should be even faster. Depends a bit on what exactly you're dumping. So I did measure something. Okay, I'll get to that, but it should be fast. Next, it must expose detailed information. The thing is, if I wanted to replace the implementation in make dump file, then I have to provide all the details that make dump file needs to produce a filtered dump, which was the reason I implemented these attributes, because otherwise it's not really extensible. I would probably have to create a data structure that gets updated whenever the format gets a new version. And the disk dump already has something like 10 revisions. So yeah, it gets extended from time to time. And last but not least, it should be reasonably easy to use. With that, I mean, the API should not be overcomplicated. I think I did not quite meet the goal, but given all the other constraints, well, okay. I definitely accept pull requests that provide an easier API. And even like feedback, if you have ideas how the API should be changed to make it easier for the users, like just let me know or open a GitHub issue. Good. So next, the challenges. Okay, why it can't be replaced today? Well, apart from the design goals, which are a bit ambitious, we have this architecture zoo, and although it may look like, yeah, libkdump file supporting 5 architectures already is pretty good. If you compare that with the other existing tools, it's actually less than a half. Even though we probably can remove one line from this table now. It's still less than 1/2. The 31-bit. Yeah, I probably can also forget about the 31-bit S390. Yes. Now, the thing is, adding architectures is relatively easy. When I added the 32-bit ARM, I wrote a how-to, like I was recording the steps that I was doing, and it's available. It boils down to implementing the page table translation, or whatever the hardware does. That's why I don't consider the IBM Power support ready, because okay, you can have Radix page tables with recent Power CPUs, but there's also this H tab, like a hash table, and that's not implemented. So I mean, okay, whatever. So it does not have to be page table translation, but usually it is. Then you want to write some code that will support the Linux kernel. Mainly that is interpreting the data from a VM core info and setting up the page tables automatically based on that data. And then you probably want to expose the CPU registers if they are saved in the dump format. So that is relatively easy. Except I wanted to keep the library reliable, so you always start by writing a test case, and this can be annoying. I have just started writing support for RISC-V64. Writing the test cases took me the whole flight from Europe to the US, and writing the page table translation, I did that in one of the breaks yesterday. So you get the idea. But that's because writing the test case also means finding out how exactly these page tables are implemented, reading the specs, and so on. So, I mean, if you're familiar with the architecture and not a newcomer like I was, then it's probably easier. Good. So that's the architectures. But we also have the format zoo. That's not really relevant for make-dump file, because make-dump file will always get its input data in as an ELF dump, like proc VM core. That's how the crashed kernel presents itself to the crash dump taking kernel, the panic kernel. But if, and now that is a big if we could also replace that in the crash utility, then we probably would have to support all these formats, because otherwise they would say it's a regression, missing feature. If you look at the formats, there's 3, I divided that in 3 groups, like the common ones, and that again on bare metal, the ELF is the canonical format, kdump or the modified disk dump, that's what is produced by make dump file, and that's pretty much all that we get. For the virtual environments, we have a bit more variety. There's this QEMU. Like I'm talking about, QEMU can also save a kdump format, but the crash utility supports reading a QEMU VM state file, which was not invented for taking a dump, but it's used to restore a VM state. So obviously you can also make a dump file from that. Libvirt is just a container for that. ZenElf is supported. XCore, XCSave, these are just some Zen formats that I don't know much about. Then there are these vendor-specific formats, like these are implemented by firmware. So theoretically, you get them. SA dump is like standalone dump. It's implemented on Fujitsu Primergy servers. There is no documentation for it. Oh, actually there is, I wrote it. I reverse engineered the format based on a few samples and wrote it down. Otherwise, Fujitsu was not very open about sharing the details. There's this RAM dump, that's a Qualcomm thing, and a bunch of mainframe formats. Yeah, S390 dump is even supported, ZVM is not. And then there are some historic formats which probably don't have to be re-implemented, but as it happens, LKCD was implemented initially, so that is, and disk dump is just an older revision of the kdump file, so that is also implemented. So we have the history is already keep, like nothing more to do. The problem with adding formats is there is no how-to. So if you're interested in adding a format, then yeah, fingers crossed. It requires some knowledge. Like maybe you would have to enhance the infrastructure in libkdump file itself. So and some of them are poorly documented. Like kdump is defined by the megdump file sources. There is no formal specification of it. Sadump I have just mentioned. Good. Yes, so I'm getting to the current conversion proof of concept. I did try to convert megdump file a few years ago. That was version 168, which is now some 100 commits behind the current main branch. That was good. Like the easy part was converting file reads. It was really like converting a few call sites in megdump file, and that's it. Then there was address translation, which was mostly fine, with a few exceptions, like this standalone dump and Zen. They needed more adjustments. And then there was, yeah, the VM core info, which megdump file tries to interpret on its own. That was messy, but it could be done. Like, okay, I did it. It did work. With the exception of Zen dumps, it was even just as fast as before the conversion. And yeah, it is compliant with the current development trends in Linux. Like if you see, that is net removal of some 3,600 lines. So maybe it would be acceptable now to use the opportunity. But yeah, a few things are still missing. So first of all, I would have to rebase it on a current version. So I plan to do it. Good. And since we have still some time, I will present some other wild ideas. The first is not really wild because it's working now. It's a GDB server based on libkdump file. So what it does is it starts a GDB server which presents the data from the dump file. So you can connect to it and get a standard GDB session. Written in Python originally, the author. It's written by Alexander Kamensky. I don't know if he's here. No. I kind of thought he sent a pull request for the main repository, and I felt like I feel it does not belong to there. I didn't know what to do about it because the idea was so good. But yeah, so in the end, I just took his commit and converted it to a new project, which is under my namespace. But I also feel guilty about it because now it seems like it's my project, but it's in fact his. But you can try it out. It works. I have fixed a few things, so it's now also reasonably fast, and I would be interested in some feedback. What it can do full back traces, like from kernel to user space. That's a cool thing, which only works because most architectures have can distinguish between kernel and user space addresses by the highest bit. There are some architectures which don't have that, and then I think it can't really be fixed. Yeah, you would have to keep some kind of tag with each address if that one is kernel space or user space. Good. So that's the GDB server. And okay, another wild idea which appeared many years ago and was like, that was a question from an IBM engineer. He asked, okay, this library looks good. Is there any write support? Which was surprising to me because I was not thinking about write support, but maybe it could be implemented. I mean, when I redesigned some of the internals, I had that in mind, so I provide a way to make a copy on write clone. The idea is you open a file, you clone it, then you change the file format attribute, and then you can write it in a different format. But yeah, like that's not implemented. I would be really interested if anyone has good ideas for the API. But if we did that, make.dump file could be reduced to just like open it, filter out the pages, adjusting the bitmap, and then just flush it through libkdump file, which just sounds somehow interesting. If it reminds you of BFD and object copy, yes, it goes in that direction. Obviously, there are some unresolved things like split dump files, because make.dump file can produce multiple dump files. I don't know if that feature is widely used, but it is there, and we would have to think about it in the API. Yes?
Can you repeat what is write support? You convert. Repeat what write support is. You convert from a format and another.
Yeah, yeah, that's it. That's it. Like let the library write out a new dump file based on some data that it has, which could mean, yeah, use any file format that is supported for writing, and possibly also leave out some pages. Take care of the compression thing and like a lot of other things, but because it turned out the IBM engineer maintained a tool that can convert a mainframe VM dump to make.dump file, I believe. So if we had this, he could just drop that project and save some work. Okay. I'm not actively working on this feature, just to make it clear. It's just on my agenda, theoretically, one way that could be extended. So that's about it. We have some 5 minutes for discussion. All right. Omar, take the cube. Uh-huh. Okay, while we are waiting for them. Okay, it's working now.
Thank you. All right, any questions here? Ooh. Throwing you off. Alrighty, yeah, go for it.
Okay.
So Dragon is a happy user of libkdump file. A couple questions I had that I haven't gotten a chance to ask you before is you have all the address translation routines implemented for different architectures. Dragon also has them because we need them for some of our helpers. How like separate are they from the rest of libkdump file, so we could maybe use it?
Okay, so that idea actually originated from a discussion with Jeff Mahoney, and I realized, yes, indeed, there is distinction between the address translation and the interpreting the format itself, like the file format. And they are separate. You can use address translation without like KDOM file, and it was designed so that you could implement a virtual to physical command without understanding the underlying data structures, like even how many levels of paging there are. Just start it, make one step, print out the raw data, make another step until you get like indication that there are no more steps needed to have the virtual address. So it could be converted. I kind of regret that Dragon is not using that and re-implementing it for every new architecture and every new paging form that is added to an architecture, because my idea was we could save that, we could just do it once. Shall I just convert it and send a pull request?
There's a few architectures, and I need to take a look at your API to figure out if it would work for the other things we use it for. Like we also use it for user space address translation. So I'll have to think about it, but that's why I wanted to ask to see if it was possible.
Yeah, I mean, internally the address translation is implemented as a like virtual memory map that is split into regions, and each region can have a different method that is used for the translation, which means you can divide the address space into like lower half and upper half, and assign the kernel translation method to the upper half and a user translation method to the lower half, and then it will automatically work.
Okay, nice. I think another reason I didn't use it initially was because libkdump file wasn't packaged for every distro, but as part of getting Dragon into every distro, Michelle and Davide packaged up libkdump file as well, so that's no longer really a concern. So.
Yeah, that's the reason. I mean, I wasn't sure if you want to do this because it adds a hard dependency on libkdump file.
Still need to think about it, but thanks.
Good.
Any other questions? We have a minute or so. I'll add my own here. You mentioned in the architecture support that you talked about page tables and then the Linux support as a bullet point, but it's kind of interesting because it can be a little complicated to find the page tables just given a VM core info and the core dump itself. Do you have any trouble with those, or do you have any thoughts on whether it would be nice if there's a less architecture specific way to get at page tables for an architecture? It's like you have to do some weird math on a lot of different symbols that are in there, right?
That is almost correct. So the thing is, for example, for the makedump file case, there is no such need because the ELF, like the proc VM core, contains both virtual and physical addresses. So if I get the virtual address of the root page table, I just can read it with no translation. I mean, that's also a difference. Like internally, libkdump file knows which address spaces are directly supported by the file format, and it will use the one that is available. On the other hand, you may have to translate physical into virtual, which means you have to set up the direct mapping, and that will not work with the VM core info. Yes, if we could unify how this gets, yeah, I mean, but it would only help to the future because right now we have to support what is in the wild, and there is a lot.
Yeah.
And for example, like when I was writing the support for the RISC-V64, I realized the 6.4 kernel can't be supported at all because it does not export all the necessary information.
Yeah, I get it. All right, we're going to have to cut now so we can get Omar a chance. So thank you again, Peter.
Good, how are you?
It should be there. Screen. Raylan, don't let me down. If I can get everyone's attention, we did go right up to that time limit, so let's all give Omar our attention for his presentation on Dragon, writing to memory, and breakpoints.
Hi, everyone. Thank you all for coming. So my name is Omar. I'm on the kernel team at Meta, where I spend most of my time on Dragon now, in addition to using Dragon to debug our production issues. So it's been nice having both sides of the development and then using my own thing and then having that feedback loop. So this is going to be, what I'm hoping that this will be is more of a brainstorming session for how to add this feature of being able to write to memory and the related feature of being able to do breakpoints. And in particular, how we could do this in production, as crazy as it sounds. So since there are some people in the audience who aren't familiar with Dragon, I'll do a very brief introduction. I've given talks before where I've gone deep into it, but this will be a more pared down version of that. Then I'm gonna get everyone on the same page about what I mean by memory writing and breakpoints, and in particular justify why we want to do this in production. And then the main thing I'm hoping to get through is come up with some ideas for both the mechanism for how we would do this and the API, make it friendly enough, but also not so dangerous in the sense that you won't accidentally do something that you didn't mean to do. So Dragon is what I call a programmable debugger. So the idea is, instead of having like a built-in commands, it gives you some building blocks. So representations of variables or types or stack traces from the program. And then you can use those building blocks to make fancier stuff on top of that. So for example, we have a big library of kernel-specific helpers, which are basically functions that are built on top of the Dragon core that implement ways to get information about specific kernel subsystems, whether it's finding task structs or walking through slab caches, stuff like that. And then on top of those helpers, you can have your interactive debugging sessions be fairly complex, walk through a lot of different data structures as you're trying to figure out how everything fits together. And another really nice part of this is you can then pull all of that stuff that you did manually and save it in a script so you can reuse it the next time you run into a similar problem. And you can also share those scripts with others as kind of a information sharing, learning experience type thing. So I'll do a brief demo. How legible is that? Cool. So this is just on a VM I have. You can look up variables using this syntax. So for example, init task is the task struct for the idle swapper task. It prints it out as a structure, and not only can you just print stuff out, you can look at specific members. You can treat the members as if they were the same type in C. So I can index into an array. I can do arithmetic on variables. And then I mentioned those helpers before. So you can go look at the long list of helpers on the Dragon documentation. But one of the helpers we have is for each task, which lets you loop over every task struct in the kernel. And let's actually look for a specific task. So I'm just going to start a cat process over here. I can get the string representation of the command line for this task. Then I can see if I found the task I'm looking for, which is the cat process. Then let's just print something out to let us know that we found it, and break, and we can look for something else inside of that task. So we found that task. Now we have it available here. And we can do something like get its current stack trace. So this prints stuff out, including inline functions and line numbers and everything. And you can also look at specific frames. So frame 10 is this frame for VFS read. So we can get a little more information about it, but more interesting is that we can ask for what local variables and parameters are available in that stack frame. And then I can look at a specific local variable if I want to. So for example, this is the file that cat is trying to read from, which is, if we look at some of its members, we'll see T2Y pops. So it's trying to read from the T2Y. So that's kind of the quick introduction to Dragon. You can see how you can build much more complicated things on top of this. We have a collection of contributed scripts, which are just like people's debugging sessions that they threw into the Dragon repository in perpetuity, and you can take a look at those, or the Dragon helpers themselves. But everything I just showed you is read-only, so you can read any memory from either your live kernel or from a core dump. But in the live kernel case, users have been asking me for this for a while, to have read-write type features. So being able to overwrite the value of a variable, or much more powerful is being able to set breakpoints and like pause at certain places and then look at your local variables, stuff like that. And you can definitely see how this makes sense for like development workflows. So you could have your kernel running in QEMU. You could attach to it over the GDB stub interface it provides, and it would be really nice for Dragon to be able to basically control the stopping and starting of the different threads on there, and as you're like writing whatever new feature, you mess something up and you just want to do a quick like, oh, let me just set this variable and see what happens, just for debugging purposes. That's like standard feature in user space debuggers, so that would be really nice for Dragon. So I have a couple of ideas for what the API would look like. So for memory writing, the general idea is at the most basic level, you can just have a byte buffer and you can write it to an address. And it's up to you to figure out where that address is and how you want to marshal your data into it. But then on top of that, there's slightly nicer, more user-friendly way that we could do it, which is get some objects. So for example, we could get the user struct for UID 0 and get some member of it that we want to overwrite. So locked VM, I think, is an atomic long T in user struct. So its actual value is in counter, and we could just say overwrite it with this value. And then Dragon will take care of like turning that into the 64-bit signed integer and writing that to the address of counter for you. So a little less error prone. And we could even do more complicated types like structures. You could give it to us as a dictionary. We can turn it into the byte buffer and then write that. So that's what I envision the API looking like. Up for debate because I haven't implemented it, but that's the general idea. Breakpoints are a little more complicated, but not too much. So there are a few ways you might want to set a breakpoint, either by address or by a function name. Could even do a function name plus an offset, since that tends to be more stable than addresses, or probably the most user-friendly way that people are used to from user space debuggers is just give me a file name and a line number. Dragon will figure out where that is and set the breakpoint. And then this is like at its core, it's kind of a synchronous event thing that can happen. Like you set a breakpoint, at some point a thread may or may not hit it. So the API would probably look something like wait for the next event to happen. That event gives you some way to get the information about the thread that hit the breakpoint, whether it's a stack trace or local variable that you want to get, and then you can send the thread on its way and wait for the next one. There could be other events that we could handle, whether it's a thread panicking or this would also map to user space use cases of like setting ptrace events of like threads exiting. But that's the general idea. This is more or less what I imagine that the API would look like. Again, let me know if you have different ideas of what you think would be easier to use or other use cases that wouldn't be covered by this. Yeah.
Often when I care about like breakpoints, I only want to know when a function is being called from some other function. So like a really common function that, I have part of the path and I need to know the rest.
Okay, so the easiest way to do that would not necessarily require extending this API is you go ahead and get the stack trace and you check yourself, was I called from this function that I'm interested in? And if not, just resume it immediately. Boris has a question.
Watch points?
Oh, so for like memory? Mm-hmm. Yeah, that would definitely be useful as well. And I guess that would probably just be another method on prog.set watch point of your address. We could probably accept an object as well, and we'll just do it for you. And then it'll just be another event that you can get from prog, like get event, I guess. Yeah, so the nice thing about this being programmable is like there's a bunch of use cases that would be covered just by using the regular Dragon APIs to like filter stuff out. And then if something becomes popular enough or common enough of a case, we can probably add a fast path for it that like, I don't know, uses BPF to filter it out before it gets to the breakpoint or something like that, which would be faster. So thank you for those suggestions.
Yep. Have you considered using this for error injection for testing?
For error injection.
So that you could test use cases that normally don't get hit and only occasionally trigger them, not every time you hit the breakpoint.
Yeah, so I guess you could set a breakpoint on like the return instruction, clobber RAX and say, here's your error. Yeah, so I guess that's something that is not covered by this, which is overwriting registers. So hadn't considered that, but that's a good idea. Cool. Right. Cool. So if that's it, I'll move on to why we want to do this in production. So like I mentioned, this is obviously a useful feature for development. No one's gonna get mad about that. Lots of people have been asking for it. But at Meta, we've had a few cases, probably more than a few, where we've run into a kernel bug and we've come up with like, whether we've come up with the correct fix or not, we know that if we could just overwrite this piece of memory, we could mitigate this bug long enough for like the team that's being affected by it to be able to like go back to sleep because they were woken up in the middle of the night for whatever. So you could imagine reference counts that leaks because you forgot to handle some error case and now something is stuck because you're not trying, because the reference count isn't going to 0. Counting overflows or underflows. Now you have some like negative number in some accounting path, like the locked VM thing I showed earlier, and you just want to be able to fix it. So to give a concrete example, we had an embarrassing bug in Btrfs a couple months ago, where we thought we were enabling our asynchronous discard mount option, but it turned out that we weren't enabling it all the way. We set the mount option flag, or we were setting the mount option correctly, like in our configuration in FS tab. Btrfs was parsing it, and we were setting a bit in the file system information that says we set this mount option flag, and we thought we were doing great. And then suddenly we start getting reports of like our disks are really slow now, like what's going on? And we go look at some metrics, and eventually we figure out we haven't been discarding anything. So after some heroic debugging, some of the people on my team figured out we set the bit that said the mount option was set, but we didn't set the bit that actually tells Btrfs to issue discards. And like I said, that was really embarrassing. It turned out to be a case where when you were remounting a file system from read-only to read-write, we weren't doing that second part where we say, okay, discards are enabled, set that bit. So the fix was obviously to fix the kernel to handle this read-only mount to read-write mount transition and actually set the bit. But in the meantime, we could have just deployed, or we could have just run a Dragon script on the affected systems that would have set that bit manually, and that would have worked fine. Obviously, there are a lot of caveats with doing this in production. You have to be very careful about what you're overwriting and when you're overwriting it, because like race conditions are definitely a thing. And it's not meant as a replacement for a live patch. It's more of like, before you get the live patch built and deployed and everything, just do this one quick thing. And obviously, the correct thing is get your live patch out, get your actual kernel update out. But in the meantime, we can do this. So hopefully that explains why I want to do this. So now the tricky part is like all the crazy reasons or all the crazy ways we might be able to do this. So for development, the answer is easy. It's just do it over the GDB stub that QEMU provides. But there's a bunch of different ways we could do it for production systems, and this is what I mostly wanted to get people's ideas about. So I'll list a few of the ones that I came up with so far, and that I've brainstormed with people leading up to this. So this first one is almost a joke. Bring back DevKMem. I don't know, there was an LWN article early, I don't know, remember if it was this year or last year, about celebrating that we finally got rid of it, right? So DevKMem, for those who aren't familiar, was basically a virtual file where the offset was a virtual address in the kernel. You could read any memory from it, and you could also write any memory to it. And it was basically this beautiful thing for rootkits. And Dragon is not a rootkit, but it has some things that might be akin to a rootkit. And anything you make easier for debuggers also makes it easier for exploits. But anyways, that is the most straightforward way to support this. But I don't think anyone is going to accept that patch. So alternative is a custom kernel module, which is basically DevKMem, which is not that much better, but Dev crash, yeah, yep. But at its core, like you need to expose some way that's just like write this arbitrary address with this arbitrary contents. And I think the trick will be providing this, but getting the access controls on it right. So I'll get to that in a second. But the other potential way to do this is integrating with KGDB. So we don't have KGDB enabled in our production kernels, but it's not the worst thing we could do. So KGDB could be used for memory writing and for breakpoints. it's kind of the backend for the GDB stub. So it already supports these operations. The tricky thing is it was never intended or designed to be used from a live system as it was running. As far as I could tell, someone correct me if I'm wrong, but I sat and tried with this for a little while, and I couldn't get KGDB set up in a way that it would just let the system keep running while I had like set breakpoints or was trying to write memory or anything. You set a breakpoint and it stops every CPU. So you can't be running Dragon at the same time that you're in this breakpoint. So maybe it would be possible to fix that, or rather extend that to only stop a certain CPU and let the other CPUs go ahead and run Dragon. Another idea is doing this with BPF. This is a question mark because it kind of goes against everything BPF believes in, which is that your program should be safe.
Peter? So why is using KGDB a bad idea if it stops all the CPUs? Isn't that the whole point of KGDB? I mean, you would be able to then probe and do things in an atomic sort of way. You don't want to have other CPUs messing with the state while you're looking at it through KGDB.
Yeah, so that makes sense for the case where I have another machine that is debugging this machine, like the virtual machine case. But I want to be able to, or we need to be able to run Dragon on the same machine that we're currently debugging. Like the straightforward interface is, let me start Dragon, just do this prog.write whatever, and it overwrites the memory of the kernel I'm running right now. So that's why Dragon is running in user space. It doesn't have any special permissions that lets it keep going while KGDB is going. So we can't have everything blocked. We at least need Dragon to be able to do its thing.
Yep. For me, the question is when you keep running Dragon on the same kernel that's being breakpointed at some function, how do you guarantee that Dragon doesn't call this function as well?
Yeah.
And then get stuck as well. So it's sort of chicken and egg problem, I believe.
That's why
I think we're back to having a second machine, though, right? Yeah.
That's why this is difficult.
No, it's not. I mean, that's how you normally use KGDB, isn't it?
That is how you normally use KGDB, yes. But and we could probably get away with it on our machines over like the out of band thing. But like I said, I'm hoping to have a way to just do this from the local machine. So to get back to what Philip said, bullet point here, that the idea I had for that is have a watchdog that basically bails you out if you deadlock. So like if the kernel is in a breakpoint and then Dragon gets into that same breakpoint and it gets stuck for too long, the watchdog sends an NMI or something and says, sorry, your breakpoint got canceled. Just keep going. That's the best I could come up with for that, but yeah. Did you have another question?
No, just another question. Have you considered something like K-probes? Then you don't have maybe the full control on where to use breakpoint, but at least function start and function exit.
Yeah, and actually, I thought you could set some K-probes at arbitrary addresses. Yeah, so K-probes gives you a way to like hook into an address and do the breakpoint. And I guess at that point we would probably still need a kernel module that implements the like call out to Dragon and let it know that you hit a breakpoint, right? And then you could still do the watchdog thing. So yeah, that's a good idea.
So another wrinkle with this is that lockdown is intended to prevent that, which I assume is enabling a lot of production kernels. So it's meant to prevent any unauthorized changes to the running kernel, even by sysadmin, capsys module. I see you have keyring down there, so maybe you're getting to it, but I just wondered if you had any ideas about working around lockdown or working with lockdown.
I would probably say if it's locked down, we just wouldn't do it. I think it probably would be frowned upon to try to work around it in any way, and in theory, it shouldn't let me do it in any way, right? Yeah. So you just mentioned access control. So one observation is, in most cases, anything that Dragon would let you do with these like terrible ideas would be you could just do by loading a module manually anyways. So perhaps Dragon should just let you do whatever you, or maybe not Dragon, but the underlying mechanism, perhaps it's good enough for it to be controlled by capsysadmin or capsys module, with the caveat that some people run with mandatory module assigning. So capsys module is not necessarily enough for you to be able to load an arbitrary module in. So there's that caveat, and there's a caveat of like part of the reason people hated diffkmem is that it made it too easy for like anyone that happened to get root to be able to own the whole system. So that's why I'm thinking that the capabilities might not be enough. And my very vague bullet point of keyring is like, maybe we need some mechanism for whether it's the custom kernel module or whether it's adding this access control to KGDB, whatever the underlying mechanism is, we might need a way to say the user that's running Dragon authenticates that not only my root, but I'm like special kernel team root that actually has permission to do this. And kernel keyring or some other module or some other like signing thing might work for that. Does anyone have any better ideas than that?
Sorry, it's probably not a better idea. It was just a what about. And you might encounter some issues in terms of Dragon or Python just loading code, right? Because there's so many pieces of code that can get loaded by Python. And if you wanted to really be confident that this is safe to do, right, then you'd want to validate all the code that gets ingested by the Python interpreter to make sure it was what you intended. Otherwise, there's no reason I couldn't have put, a dummy module in your Python path that's decided to do something bad.
Yeah, so that kind of ties into Boris and Song's FS Verity and BPF LSM thing. Yeah. So yeah, I mean, that's why I kind of copped out and made it like a per user authentication thing, and like user has to be careful about this, but like we saw where that gets us with like SUID binaries.
So the other option, instead of like, full on breakpoints, is to define the limited set of things you can do when the breakpoint triggers and turn that into a BPF or a kprobe or something like that. So you'd have to write code that you then insert, but you wouldn't have to stop the code.
So the limited set of things that you can do is still like write kernel memory, right? So that still needs to like get through. We still need to convince someone that like for some BPF programs that are loaded by, or that are controlled in some way by like keyring, whatever, they can do this.
It doesn't change security, it just changes the stopping machinery. You don't have to worry about stopping. Sorry, it doesn't change the security part, it just changes the complexity of stopping the CPUs.
Right, yeah. So then you don't need to actually worry about this deadlocking with your own breakpoint problem.
We have one question from chat.
There's also a comment from chat. Maybe Dragon doesn't need to get the full interactive control when the breakpoint is hit, but can inject code at the breakpoint for what it wants to be instead, or wants to do instead.
Yeah, that makes sense.
Like
That's similar
system
to what
tap.
Chris suggested, so that makes sense. Cool.
We're at time, but if you wanted to wrap up quickly, another minute or two.
Yeah, that's pretty much all I had. So I guess I still have more questions and answers, but come find me later, and I can and we can talk about some more bad ideas, or I can just show you cool Dragon stuff.
Thank you, Omar. And the break is at 11 if you want to find Omar, or you can steal him away now. I don't know. I'm gonna give like 30 seconds or so, let people get settled. I know people are coming in and out, but we will get started in just a second. All right, we're gonna call that good. Hello, everyone. I am Steven. Was up here a few times before already, but I'll also be talking. I promise there's no conflict of interest here, running the MC and also being a speaker. It's fine. So don't worry here. But yeah, so I'm going to be talking about debugging with formats that aren't Dwarf, essentially, especially how it relates to the Dragon debugger, and not just Dragon, but that's going to be a large part of it. I mean, it's going to be the entirety of it. So yes, just Dragon. And I'm going to start to motivate the problem and kind of give the goals, what we want to do with Dragon, and then kind of open up to discussion to try to understand what other people's problems are. If they have problems with debug info, how we can build this to be the best solution, not just for the use cases I have, but hopefully for others as well. I'm going to grab water because my mouth will get dry. Okay, so to give the kind of motivation, I work at Oracle on the Linux sustaining team, and sustaining refers to the software. We're finding bugs, fixing them, making sure our customers are happy. And that means that if our customers encounter a bug, they have already configured kdump, and they give us a VM core. We go onto our secure servers. We do an analysis with Crash or Dragon. Historically, there was a lot of Crash. It's becoming more and more Dragon-oriented, and that's been really fun to see. It's a lot more flexible for us, but frequently it's not that simple. Sometimes you can't just open the VM core, do a 30-minute debugging session, and I found the bug. That's it. A lot of times there's more. There's some back and forth with the customer. You need to maybe do some debugging on their system, and that's hard. Customers, do not like their systems being debugged, especially staging systems are better for that sort of thing, but they don't like that, and it's hard to do. Internally, we get to have a shared debug info repository somewhere where we can just pop open a VM core and find our debug info, and we're working. We don't spend any time thinking about it. But on a customer system, you need them to install debug info, and that means, do they need to configure a debug info repository, or do you want them to install it to the system or download an RPM? There's a lot of stuff going on there. And customers also don't like having debug info on their system. Sometimes that's policy. I don't know what the policy is, but I've learned not to ask or try to reason. In those situations, I move on. They're battles you can't fight, especially when you're being paid to fix problems, not add more. So that's one motivation I have. But another motivation is new users to Dragon. Debug info can be a bit of a brick wall for people. You say that you heard of this new debugging system, it's cool, but you want to try it out, and you need to install debug info, and some distributions, you look at the Dragon documentation and it's great, but some distributions just don't even have debug info for the kernel. This one would be Arch, by the way. It's frustrating, but yeah. And then other distributions, they have it, but it's a long list in the Dragon documentation. It is great, but there's a long list of steps you need to take. Which distribution are you on? Do you need to set up a repository? If you install the debug info package, is it going to get updated with your kernel, or are you going to have an old debug info sitting on there next time you upgrade the kernel? I don't know. Have you used that feature of Yum? I forgot. Similarly, you could use debug info D. Does your distribution have one of those servers? How will that work? How will you delete it once it's gone? So it can there's a lot of complexity here, and I'd like to see a world where, maybe, oh yeah, I'm getting ahead of myself, but I'd like to see a world where we can make that easier. Another kind of motivating factor I have here is that Dwarf is big, and this is just based on the files that I had on my laptop actually, but for say a VM Linux, the core kernel in our distribution, the debug info size can range from 400 megabytes, hey, that's not too bad, all the way up to a gigabyte, just for the VM Linux. And then let's talk about kernel modules, depending on how many you've got loaded. That can add a few hundred more megabytes. And to be clear, I'm not trying to cast any aspersions, be negative about Dwarf, because for the price, you get amazing features. You get source code mapping, you get call frame information that lets you look at, I mean, Omar just demonstrated getting variables out of stack traces, you know, without any work. I remember when we were like reading assembly to get those because Crash couldn't get it for us. So, you know, really great stuff, but the majority of the features that you're going to rely on in a script while debugging are probably just needing three things: a symbol table, so you can look up a global variable; some type information, so you can interpret that memory, that variable; and then maybe, and this isn't even a maybe, you might not need it for most scripts where you're just, you know, wanting to read memory, maybe write memory. You might not even need a stack unwinder, but it's still a good thing to have. And you probably don't need variable access if you do want a stack unwinder. So now is the time to talk about goals and observations here. The kernel already has a symbol table, and I don't mean the ELF symbol table. It has KLSIMs. And I don't have the little table to show you, but pretty much every distribution on Earth supports KLSIMs all, which is not just exported symbols, it's every symbol in the kernel. So you can pretty much rely on that for distributions. The kernel also expects to have a reliable stack unwinder, so as reliable as you can get in the world of interrupts and asynchronous stuff. So you've already got usually frame pointers, but on x86-64 orc, which is very cool stuff. And finally, there's sometimes type information that's outside of what you have from Dwarf that might be BPF or BPF type format. Many distributions are coming with that enabled, and on UEK kernels from Oracle, we actually have, it's just maybe a few hundred line patches in total that add support for CTF that is otherwise built into all the major tool chains. And CTF I'm going to get into a little bit more because that's going to be a big part of this. But the main point here is that the kernel already has a lot of this stuff available at runtime for you if you know how to take advantage of it. So what I'd like to see is kind of a mix and match approach available to people who are using Dragon. You have symbol tables. You could get it from an ELF file or from KLSIMs. Modules have exported symbols that you can look at in the structures, and they also have module KLSIMs, so you could use those. I'd like to see a pluggable way that you could choose other types systems like CTF or BTF in addition to Dwarf. And if I didn't make it clear enough beforehand, big fan of Dwarf. Not trying to replace it here. And if I'm debugging a customer VM core on my own debugging server, I don't want to use these features because I want to have source code mapping. I want to have CFI. I want to do all that. But this is a kind of an 80-20 thing. You can get 80% of that functionality with 20% of the cost if you just cut it back to just a few things. And that's what I want to see enabling some really good stuff out there. So, oh yeah, just some examples of what that might be. You could go fully dwarfless. You could have CTF, KLSIMs, frame pointer or orc unwinder, and no debug info file involved. It might be that you have the VM Linux, but you don't know where the module files went, and you can add some symbol tables from the existing information, and you can get some more information about those modules. Maybe even use BTF for that. And then example 3. It's maybe not as practical, but it's something I always thought was fun, is if you could have a standalone VM core that everything you needed to interpret it was actually already included in the core dump. You could have KLSIMs inside of it, BTF built into the kernel, and the unwinding information is all part of it as well. So you could interpret everything in there and debug the basics without downloading any other file. You just run Dragon and you're looking at it now. So those are just some ideas of what I'd like to see out of this. So I think probably more people are familiar with the BPF type format, but I'm going to talk a little bit about CTF here because this is something that's been really exciting for me, and it's been something that we've already packaged internally at Oracle, and we've been pushing upstream a lot, and we're getting some traction on, I think. So compact type format is the compact C type format in particular. It's already built into GCC and GDB. I don't have the exact versions, but I know people here do. And it's built in, so you can generate it with GCC like normal, you can run GDB like normal, and you can use it as if it was dwarf, except for the features it doesn't have. And normally it's not supposed to be stripped out. You use strip to get rid of the debug info, put it into your debug info packages, but in this case, it's compact, it's really small. The whole point of it is that it stays in your ELF file or otherwise stays with your main package so that at runtime, you can get the type information you need. In the case of the kernel, the way we have it and the way we've been sending upstream patches, it's a little special. It doesn't sit in the ELF file because a kernel image isn't usually an ELF file anyway, so it can be. That was a bad statement. It can be. But it usually gets packaged into a little file on the file system that's a standalone archive. And so it's not necessarily in the kernel image, but it's usually available if you are running on a live system anyway. And yeah, it describes types. Maybe not, it describes all of the C types that you could see just as well as dwarf would. So yeah, that is what CTF is. So that's kind of the goals and a little background. I'm going to talk now about kind of implementation status in Dragon, specifically for all of those goals with a focus on CTF, but BTF as well. So step one for all of this is Dragon is actually designed pretty well for a lot of this stuff. You can actually plug in type systems, you can plug in different ways to find variables. One thing that you can't plug in right now is a symbol finding system, a symbol table essentially. It's kind of built in the assumption that you've got an ELF file that has an ELF symbol table. And so we've actually got in review right now a system that's going to allow you to plug in any function you'd like to look up symbols in in whatever you're debugging. You can plug in a C function or a Python function if you want. And just to demonstrate what that looks like, here's my my symbol finder that I wrote a couple nights ago just for fun to demonstrate it. Yeah, if you look up a symbol named secret or adder 42, you get the secret to life, universe, and everything. Yeah, just a kind of. This is not very interesting in terms of showing off the capabilities, but you can see that Dragon, once you've added it in, it uses it like normal. So you can also do this in C, which will end up being a lot faster, less copying. But so that system is kind of in review. It's getting ready. And on top of that, the next thing that we would want is being able to use that plugin system to plug in KALSIMs as your symbol finding system. So we've got this also in a pull request up right now on Dragon. It's in a draft since it's based on the previous pull request. But it's a C implementation, so it's faster, and it can do it in two ways. The easy way, the maybe obvious way, is that say that you are running live against proc kcore, then you can just read proc KALSIMs, assuming you have permission to read it, because technically, root can only see the addresses, and you can actually run Dragon without root if you do some fun stuff that we recently added. That's, yeah, a separate discussion. But so you still need root, but only to open the file originally. Anyhow, the other option, if you don't want to read proc KALSIM because you're not running against kcore, say you have a VM core, is that Dragon can actually find the necessary symbols inside the VM core info note inside of the VM core, and it can find enough information about where to look for KALSIM's data structures that it can then find them, parse out the KALSIM's information. It's compressed in a really interesting way. If you've ever read that code, if you haven't read it, I would encourage you to check it out. It's not gzip, it's just a compression method that someone made up. Yeah, but it's cool. In any case, so we can do that. We don't need to use the file in proc. We can just parse the data structures ourselves. Either way works. Obviously, it's faster to just read it out of proc. But there are some issues here. Unfortunately, ELF symbols actually come with size and some other metadata, like whether it's local or global, whether it's a function symbol or a data symbol or some other type of symbol. So there's a lot of metadata that ELF includes, and KLSIMS has some of that. If you look over here, these are just a couple I pulled from my kernel. I didn't reboot, so please, I'm sorry I broke KSLR. But yeah, there's the D there tells us that it's a data, and the fact that it's capitalized means that it's global, not local. But that's the best that we get of that metadata. In particular, there's no size. Slab mutex starts at that address, that ends in 00, and it presumably continues until slab caches starts at address 20. So that's maybe 32 bytes. But if it had some sort of SMP alignment, cache line alignment, whatever, there could be a gap there. You don't know the size. So you might use the heuristic, well, let's just take the next symbol and use that as the size. Unfortunately, that doesn't work. Or if it does, then per CPU end is a really, really big symbol. Obviously, the way you can get around this per CPU is kind of special. It's x86 specific because of segment registers. You could say, well, per CPU end is the end of the per CPU section. Let's just say that's a 0 size symbol and move on with life. Or I have another workaround which sets a maximum size for a symbol, because this becomes a problem, say, when you have a pretty print from Dragon and it's saying, well, this user space address is actually per CPU end plus a few gigabytes. It's within that symbol, so you don't want that. That's why I try to avoid that. But let's see, there's another issue here, and this doesn't actually include the code changes, but recently, and by recently I mean 2 years ago, KLSIMS got updated to add support for bigger symbols for Rust, and that's pretty cool. But that bespoke compression system that I mentioned got changed, and it's a kernel thing. As long as you change the kernel and you update all the code in the kernel, the kernel doesn't necessarily care about making this easy for other people to parse. But unfortunately, that means that there's some messiness, because this isn't something people backport. At least I hope not. This is a pretty silly change, or not silly change, a good change, but it's not something that you would backport to stable kernels. So right now I've gotten away with doing a kernel version check. However, I expect a big thumbs down from Omar on that, and I need to add some sort of in-kernel versioning system, some way for us to determine what's the most recent, how to interpret KLSIMS data structures in the kernel. Omar actually has some experience with that, so it's not hard. He did that for orc. Oh, we have questions there.
Just about the per CPU end, you will never find an actual address that is that small. This is used as an offset from the per CPU base for your current CPU.
Yes, for sure. Yeah, that's the base. Yeah, it's an offset from the base, and you use the segment registers in x86 to find the per CPU. Yeah, it's not a real address, but it's good enough because Dragon expects that it can take whatever fake address you have and then find the per CPU base and then offset. So however it's implemented on the architecture, Dragon wants to know what the fake address is. So yeah. But yeah, so the way I'm working around this with kernel version checks, I'm hoping to add a version to KLSIMS so that we can do a more clean way of detecting these changes. But I caught it late, so unfortunately that means I'm going to have to try to get this backported to all the kernels that currently have this. So yeah. But those are kind of the two main issues I've seen with KLSIMS. Step 3 would be adding CTF support. And this is already, I didn't link to it, but we've got a branch up on my Dragon fork right now that has the implementation based on those previous 2 pull requests. And it's, we're using it a lot, actually. I've been using it a lot. We're testing it in a lot of different kernels. It's been working very well. So this is not just, oh, I have a development branch somewhere. This is something we're keeping updated. We're using pretty well. That adds support for CTF via binutils libctf. We're not adding, I'm not interpreting the CTF format myself because binutils standard already has all of that information. So we just use the library for it. And it's pretty simple when you think about it. If you want to look up an object, you just find the symbol, find the type for that object, which CTF knows, and then you combine those 2 information to get back a variable. So it's, pretty simple. That said, implementation not always as simple as real life, or as we would hope. So the other step 3, BTF implementation. Right now, status of that is that I have a very, very old branch that implemented BTF. And unlike CTF, with BTF, I just ended up parsing the format myself because I don't really know whether we have good BTF. I know there's libbpf out there. It seems tied to the kernel version right now, so it seems like it might be a bit trouble to link in a reliable way, whereas binutils, you have it on your system. It's also a little difficult because BTF doesn't really have a format version to it. It just is tied to whatever the kernel version is. I think there's a table somewhere that shows new features added over time, but there's not a particular format version, which means it's a little bit more difficult to open BTF in the kernel and just say, I know I have support for version 3 and this is version 2, so I have backward compatibility, so we're good. So there are definitely some things that could be done to make BTF a little bit easier for sure, but as of now, it's parsing the format and hope that you can keep it up to date faster than the kernel does. So I think that's my last slide. I have just some discussion questions here on things that you might consider, things that you might want to talk about, how large debug info sizes impact you if you're doing a lot of debugging, whether you would use any of these formats in Dragon or in other debuggers. How do you manage your debug info? Would this be something that's really useful to you? What APIs? Any thoughts on any of those things are welcome. But that's all I've got. Right over there.
So yeah, smaller runtime debug info sounds wonderful because it's a huge pain to download some of these things, big, depending on where you are at times and stuff too. But what do you give up when you if you were to if we give up using the ELP debug info? I mean, what do we get?
Good question. So the things that I highlighted, probably like slide 1 or like 3 or 4 here. I don't know if I can bring it up, but things I highlighted are essentially source code mapping is one big thing that you don't get. Oh yeah, there it is. Source code mapping is something that Dwarf gives you where you can see where each line of a function maps to source code. In terms of function unwinding, you lose some detail there as well because say that you're using a frame pointer or orc, it doesn't really matter. Either way, all those are going to give you is the canonical frame address, right? They're going to give you a stack pointer, a frame pointer maybe, but they're not going to restore for you things like inline function calls. So you could be 3 inline functions deep in a stack trace and you just get the whatever the actual function name, symbol name is, and that's the only frame you get. And then you won't get registers or variable names. So those are things I love to have in a stack trace, but they're also things that I mainly use when I'm interactively debugging, not so much that I use if I wanted to run a script for diagnostics, say for a customer. So it balances out for me, but you do lose things. And I don't know if Omar has other thoughts on useful things Dwarf does. That was it. That was it. Got another, or Philip, were you already?
Yeah, but just a quick comment. Another thing where this might be very interesting is out of tree or proprietary out of tree modules where the vendor doesn't ship debug info, then you at least have the chance that they don't strip the BTF or CTF information from the binary.
Yeah, definitely necessary evil sometimes for us.
Just an honest question. When I hear about like people complaining about dwarf being too big, I always wonder if anyone tried to just make dwarf generation more fine grained, because it's not an all or nothing. It's you can decide, oh, I just want it for global symbols and don't have all the die tree.
That's a very good question, and I've heard it come up a couple times, and that's not something I actually know, but I see Omar waving his hand. Maybe he can give some context on how possible this is.
Yeah, I think if you control the debug info, that's something that you can do. But for a lot of users that are probably just doing this from their distro, the distro is probably going to just enable everything because they don't know what tools you're going to be using on it, and then you're back at square one.
I was thinking the question in the perspective of, instead of reinventing new debug info formats all the time, like changing GCC to say, oh, I just want this slice of. I was just wondering. It's not the.
Yeah, there are options you can enable or disable in GCC right now to choose different things, and there are also ways you can deduplicate or strip down the debug info after the fact. But I don't think anyone does it on the kernel debug info. Distros do it on some distros do it on some user space packages.
DWZ.
Yeah, DWZ. Yep. But I haven't seen it done on the kernel.
Okay, thanks.
It sounds like the conflict, if you don't, is that you can either do it with GCC and not emit as much debug info, but then you lose it for all the use cases where you wanted that. But if you use something that could like selectively strip, maybe you have a better chance, but it sounds like that's not used much.
So I'm wondering if, I mean, part of the issue is not that when you build the debug info, I mean, if you would have a way to extract both a compact debug info and the full debug info, and then get both sets to the end users, then I think you'd cover both use cases.
Yeah, I think that's true. Yeah.
Yeah, and the nice thing is a lot of the things that Stephen is making use of here are in the kernel anyways, so you're not actually adding anything extra to have your compact thing. But I had a question related to that, unless you had anything else. Okay, so you mentioned that CTF is a separate archive that just sits on the file system. So does that mean that you can't use it for this, like the dream use case of like standalone VM core?
Yeah, that's correct. If you had the VM core, unless you happen to be lucky and generate a page cache that happened to have it in page cache and you didn't filter it out with make dump file, then I guess you could find it, but that's not going to be supported anyway. So yeah, you can't use it for that dream case, but
yeah,
it's kind of a very practical thing to let go, or that is a use case that I'm excited about, but I think it's a pretty reasonable sacrifice to make to have it for live use cases.
That is one thing that BTF does have, right?
Yeah.
Yeah, except that it doesn't have variables, which CTF does have.
That's something I've been letting slide for a while. Yeah, I've got some patches out there to fix that.
Yeah. All right. You mentioned debug info D as well. So Dragon does support debug info D for user space stuff. We just get it for free from libdwfl. We could do it. This is more addressing like the convenience factor. Like you're still gonna have to wait to download this huge 1 GB thing. So we could support it for the kernel as well. Except last time I checked, the debug info D client, or maybe it was a server, did something silly where it felt to me like it was going through the whole RPM every time that you asked for something. So you'd ask for a module, and then it'd have to like the server side would have to decompress everything up until that module from the RPM to give it back to you. Yeah. So it took like 3 hours.
Yeah, RPMs are not a great format if you wanted to find a random file and then get.
It's 11 now, so.
Yeah, you're right. We can take any more questions to the hallway track if that works for everyone. So thank you. We'll be back in half an hour. All right. I don't know why I'm up here yet, but Guillermo is get the messages out.
Hi, Stephen. Can you hear me? Wow.
Yes, we can hear you. Awesome. I was just coming back to communicate on chat, but that's a lot better. Okay. Okay, let's get everybody sitting down and everything. And thank you for coming back to the second half of debugging. I can assign you presenter right now, I think is what I need to do. Let me
Okay.
give you, and then what you can do is there's a plus icon at the bottom left. Okay, you're presenter now. There's a plus icon, and
Right.
you can hit that, and then you can select your PDF slides, and then you can present from your computer. Or you could, if you wanted to share your screen, that's an option. But yeah, let's get on started here when KDump is too much.
Perfect. I think I'm hearing myself super loud there. So I don't know. I guess I will turn my volume down. Maybe it's a good idea. I don't know. Okay, I guess we can start, right? Let me move this here. Okay, I'm not hearing me anymore in the room, so it's good. Thanks for AV folks. Okay, so thank you all for watching this presentation. Thanks for bringing up this micro conference. I think it's a very good idea to get everybody together to discuss this stuff. I'm very interested in that. Quite nice talk so far. And my name is Guilherme, right? I work at Igalia, which is a cooperative that works mostly in free software, open source, with an upstream first approach. And I've been working with the Steam Deck lately. In the past, I've worked in different stuff like PowerPC or in a sustaining engineering team like Steven, but in Canonical, dealing with customer stuff. So I've been always working with KDump and debugging stuff from customers and whatnot. So and here we are going to talk about when the KDump is maybe not the best fit, it's too heavy, right? Okay, use the mouse here. So the summary is it all starts with the Steam Deck console that I'll present more soon, which is a game console and has a distro based on Arch Linux, and we started to consider how to collect logs in case such system breaks like a panic. And we have some infrastructure for that, right? KDump is the most standard one. Most of you, or if not all, know that. But VMcore might be not the best fit here. And what alternatives do we have, right? I think one of the good ones that we end up choosing is pStore. It's a lightweight mechanism. And it's good in some aspects, but also has limitations. So we can discuss a bit how to improve these or some ways of mitigate that. Starting with the beginning of the thing, the Steam Deck. I guess some of you, if not all, know this new console from Valve. It's in the media. A lot of people talking about this. This picture is of my deck. It's not great, sorry. I took the picture myself. I'm not good at that. And it's a powerful computer. It's a console, game console, but in the end, it's a computer, full computer. 8 threads, AMD custom APU, 16 gig of RAM, 3 models of storage, and this slide is now outdated because in this weekend there was a release of an improved version called the Steam Deck OLED with more storage, I guess 1 terabyte, extra battery, and of course a different screen. And with the Steam Deck, of course, we have it runs Linux, and one of the best things, in my opinion, about this is the ecosystem, which is full of open source. This is the goal. And the distro it runs is called SteamOS, which is basically a version of Arch Linux with some extra package and sauce on top of it. It has a game mode, which is a compositor called GameScope, very, very nice. And you can use it a desktop, KDE Plasma. And has a complex software stack to run games like Proton, which is a wine thing, and DirectX to Vulkan layers to allow running Windows games on Linux. So what happens if such stack crashes? Like, would be nice to get logs to help to debug this, right? And what about kernel panics? Though they are rare, they should be rare, we should maybe take some action. Collect data would be nice, right? Arch Linux itself has no official tool for that. There is a very good wiki, as most of the Arch wiki, explaining how to set up KDUB manually in manual steps and whatnot, but that's it. There is no, as far as I know at least, there is no official KDUB tool. So we start to consider what logs we should collect in case of a panic happens. We can collect Vimcore, as we discussed a bunch already in this micro conference about Vimcores, but we also can collect the message or some extra information from the userland process to help debugging Proton issues if that was the trigger of the panic, for example. The thing with the Vimcore is that it might be a bit too much. The problems are it's heavy on storage, might be some hundreds of megabytes. It's a bit difficult to share. Imagine we want to share this information with the vendor, with Valve. So everybody is sending Vimcores. It's maybe too much. So maybe the message is enough with some extra information if possible. And there is the statistics factor. Imagine we have a bunch of Steam Deck consoles running worldwide and some panic here and there. They send the data, the message to the Valve server, Sentry, or something like that. With that, you could correlate and see what the code traces are more common, what is the common causes of the most issues, and that's very helpful, I guess. So we want to rely on in-kernel infrastructure for that, for collecting the logs. So what tools do we have, right, for this? The first one, which is, I am going briefly because most of you know probably, is the KDump, right? So KDump is the kexec-based solution in which we preload the kernel in a reserved area. And when we have a panic, we jump to this new kernel ASAP to collect the memory of the broken kernel using the tool, for example, make them file. So you put there the small distro and collect the log. The Vim core that is collected is usually compressed, distributed. You can remove the free pages and user space pages, so it's reduced. It's very useful for post-mortem analysis and share with support teams like the sustaining team. It's very rich data collection. You have everything there, right? The kernel memory is there, but it's not always suitable. The main concern for desktops or the Steam Deck, our specific case, is the pre-reserved memory. It's more and more lately, like the orders of 200 megabytes to make the kernel boot and with all the tooling necessary to collect. So it's reserved on boot. We can't adjust that without reboot. There was a bunch of discussions already about this, but it's very tough and some people are very against that, adjusting that after the reboot. So it's difficult to estimate as well. There is a link here. I tried to work in an estimator some time ago when I was working the sustaining engineering in Canonical. to help the customers and with some heuristics, but it's very difficult to properly estimate. It's okay, but not super accurate. And another big issue is regarding the deck and desktops is the size of the core and the privacy about this. It's a bunch of data there, right? You have the kernel structures. You can even probably infer some passwords by navigating that. Some users wouldn't like to share these, I guess, right? And there are risks. KDump is a bit risky in the boot process, especially if we don't have much control of the hardware. PCI devices might be in a state that they does not work properly in the KDump boot, right? We don't have a standard reset mechanism, especially in x86. This link here in the potential nightmares about the discussion we had in the past about the use case of stuck device that was preventing KDump. And we also might have problems exactly in the point of collecting the vim core or out of memory if we don't properly preserve the amount necessary in the crash kernel parameter, and also make the file incompatibilities with the kernel version. We need to keep track of that. That was common in Ubuntu, for example, to have a make them file that was a bit older and the kernel got updated, and then it was a problem while collecting the make them file compatibility, right? So we start revisiting alternatives. We have hypervisor mechanisms, but they are hypervisor mechanisms, right? So for virtualization, which is not our case, like FADUMP for PowerPC, QEMU, this tooling, SADUMP was mentioned in the presentation today. We have net console, zero console stuff, but this is too much invasive. It's for developers that set up the consoles and can collect data while the bank happens and see that or save the consoles using the terminal plan. But then we have pStore. pStore is technology called persistent storage. It's a pain time data collection, and it's a very flexible one. So let's talk a bit more about pStore. I consider it a lightweight mechanism. It happens exactly when the bank happens. It collects data into a backend, and then the machine reboots. You don't need to start a new kernel. It has a bunch of backends, like the RAM, which is called RAMoops. So you save in a portion of RAM, and the next kernel can pick it up. You have UEFI backend, so you save it as a variable in UEFI. You can use the CPI ERST table, or even a block device. So I never played with this. It's kind of a new, the block device one, some years. And it's very common in embedded devices. If you check some ARM boards, they have in device trees entries for RAMoops. So it's a standard there. Also in Chromebooks and Steam Deck, which we're going to talk. It's fast, hopefully transparent process, and does not require KZX support, which is a bonus in systems that have kind of locked firmwares. I've noticed that in some ARM boards that can KZX, because the firmware does not allow it, breaks it, some security assumption. But it has some cons, of course. It's a trade-off. So another advantages, some pros here. It has many front ends. You can use it not only for bank, you can use it for trace, collecting the functions of the tracing log, for console, for user space messaging. You can have you can hook some, it's called p-message, the front end, and some user space to like Proton could write some stuff that will be collected after break. It does not require memory reservation, which is a big pro for us, right? The UEFI backend zero, because it's UEFI. RAMoops, it requires some portion of the memory, of course, because it's going to write there, but it's usually very small, like 1 megabyte, 2 megabytes. The cons, the main one, you are not collecting a full vim core, right? So you lose a bunch of data. And it runs after independent fires. We are going to discuss this a bit about one of the challenges of this approach. Also, there's the tooling to configure pStore. As far as I know, maybe there's, I don't know, there is an elementary tool that's called system pStore that saves the log that appears in CSFS, saves to a folder, but we don't have ways to set that. It only works if pStore is already set, like through command line, I don't know. So we work in a tool called KDumps. KDumps is a tool that includes pStore and methods of data collection for Arch Linux. It's available in the Arch user repositories. It supports Grub and some init systems. it includes VMcore, but it defaults to pstore. Sorry, it includes KDump collection, but it defaults to pstore, and it uses remoops. This is interesting because in the Steam Deck, we have some portion of the memory, around 15 megabytes, for free. It's not used by the kernel. There's some alignment code in x86 architecture that keeps it as a RAM buffer unused. So I noticed that and said, okay, let's try, right? So I wrote the log there, the log, it's there, the firmware, we have control of the firmware. It does not reset the memory. So we are using by default the ROMs backend, but we have plans to support UEFI because it's quite useful in some cases and other bootloaders. It's default in Steam Deck now. It's able to support though another tool does that submission. We communicate with this other tool, right? But then the question remains, what can we improve in the log collection? Because the message is enough. I mean, well, can we get more information? And the answer is yes, we can use it. I found that parameter at the panic print, which allows us to write some stuff like task states and scheduler states, memory information, CPU backtraces, which is quite useful for debugging race conditions that one CPU is locking on or stuff like that, locks, timers. The thing is that it prints a bunch of stuff in the buffer in the panic time. So there's the risk that it's kind of getting mitigated more and more with the atomic work on the print case side. And panic print and the whole store infrastructure runs after the panic notifiers, right? So let's talk a bit about panic notifiers, which is a thing here. Notifier callbacks are structured in the kernel, a list of functions that can be executed in any order, right? You have multiple types, atomic one, block ones. The panic notifiers is an atomic list of callbacks that is executed during the panic time. And basically, any driver, any entity, even out of 3 drivers, can register notifiers there to do anything during the panic time. So naturally, it's risky for KDump and even for pstore. If KDump runs before that, by default, KDump runs after the panic. By default, KDump runs before the panic notifiers. So it's not a risk. But the thing is, some panic notifiers are necessary. We have a case in Hyper-V, for example. Hyper-V has a notifier that's necessary to unload some VM bus connection, they call. If that does not happen, KZAC fails and the VM is broken, right? So the solution that was found some years ago was a parameter, crash KZAC post notifiers, to run the notifiers before KDump, invert the order. And we are addressing this risk, or trying to, by a refactor. There's a presentation in recipes in the link. We are trying to reorder and better kind of limitate how the panic notifiers run. The necessary ones could run first, but the others could be really optional, right? With that, we came to the most important part, the challenges, the ideas, the discussion we can have it here, right? So pstore is a bit risky, some consider that, because of some reasons, like it runs in panic time, opposed for KDump, which is a new kernel, right? I would say the risk is variable, depends a bit on the backend. For example, for run backend, we have the risk of the firmware breaking or corrupting the RAM memory, retraining the memory, right? And for UEFI, don't have this risk. Regarding specifically this backend that we are using, the remoops one, some limitations we are finding with this is that it's not easy to reserve the memory. It requires, for example, use the mem parameter. There's no remoops reserve memory, and we need to pass exactly the address of this to the driver, the remoops driver, the address of this memory. So I would like to have a parameter. It's one of the ideas to make it easier on the users to reserve memory. Also, we have the risk of firmware corrupting, of course, and retraining memory. So it would be nice to have a test case for removes, an easy one without inducing a panic. Maybe write a variable and see if the firmware is doing that. My limited experience shows it's not common to the firmware to retrain the memory in all boots. Maybe in firmware updates or for servers. But for the desktops, which is most of our use case, and they seen that, I know that it does not retrain the memory, so it's safe to use this. Another risks we have is the panic notifiers that we are trying to address on the refactor to mitigate that a bit. And finally, no, panic print is panic print enough? I mean, it's been enough. It's a bunch of data, but is there any other data that could be collected on panic time, some structured information, or anything that could be more helpful for the bug if we only have the message? So it's open for discussion. Thanks for watching the presentation. Appreciate your attention. And that's
Thank you. I guess I have a couple questions. Also, for everyone here, if you're asking questions, I've been told, please stand up so that the camera can get your pretty face. But anyhow, or in my case, my face. So I did want to ask about the risk for the panic print functions that you're calling right now. Have you encountered interesting issues with, say, corrupted or taken locks in the panic print? How do you handle the idea that you have, I guess, when panic happens, you kill the running CPUs, and they might be holding all sorts of locks, all sorts of data. And I guess, and I know you have to be very careful in the panic function. Notifiers, that's where the risk comes from for a lot of these notifiers as well, that a lot of them aren't necessarily written expecting that they're going to not be able to get their locks. So do you have to deal with that? How do you mitigate that risk in panic print?
interesting, Cine. Thanks for the question. The thing is, I've instrumented because vStore is running after the crash, the fires by default. There's no other way. I've instrumented that. How many notifiers are running in the deck or other basic environment like x86, not a server, right? And it's really a few of them, but the risk is real because people that write with fires, they not always take the amount of care with the locks, as you said. So part of the refactor could be split in two parts. One is what I mentioned, that we want to reorder stuff and see what is really necessary notifiers to run before, etc. But the first part was a bit simple. We tried to go to all the notifiers in the kernel, that all the notifiers that exist, and check the code and see if they are doing risk stuff. And a bunch of them were doing risk stuff, like taking the locks. So we changed that. For example, they spin a tri-lock, the tri-lock alternatives in Texas. So now what happens when we change a notifier like this is if it tries to grab the lock and the lock was taken, it fails. It does not run the notifier, right? So in the field, I'm not aware of those issues in the CDEC. In my tests, I could not face any of those issues, but we are aware that they exist, at least in theory, and try to address them proactively by changing the notifiers. Not sure
Sure, makes sense. Thank you. Yeah, that covered it.
Yeah, so I'm Grant Grandler. I work on the Chrome OS, and so thank you for calling out the fact that we use pStore, because that's actually a valuable tool for us to help track down issues that customers are reporting, and including noting that there's a lot of privacy issues around that. We don't just send the pStore dump straight to Google. It gets filtered, and people have to approve that they send it. My question is about what you asked the very last at the end. What data could you add to a pStore dump that would make it more useful? And this revolves around the fact that there's sort of two kinds of crashes that happen inside the kernel. One of them is a precise crash, where you have like a data page fault, page zero reference or something like that. You know what the address is, you know what the stack trace is, you know what happened. It's the imprecise crashes that suck rock hard, right? You don't have the actual context of what crashed, but you have or that caused the crash, but you have the aftermath of like a hung task detector coming in and telling you, oh yeah, 120 seconds ago, your system got wedged on something and hasn't moved any forward, so we're gonna crash now. If someone smarter than me, I hope, can figure out how to unravel the dependencies between the hung task and what it was involved in, what context it was involved in, adding that to the pStore would be valuable, right? Because that's what's starting to collect in some of the Chrome OS crash dumps that I've seen or looked at in systems. Over time, these hung tasks become a bigger and bigger portion because they're harder to solve. So if somebody has good ideas on that, I think that would be a good addition. Thank you.
This is just my take on this. I cannot say as a full expert on this, but I had problems with hung tasks in the past as well. They are difficult to debug exactly because for the reason you said. And one thing that helped me, and we are including that in the Steam Deck, is the CPU backtraces and the tests, because you have all CPU backtraces. You can see what were they doing right in that moment. We have all the tasks printed. You can see the status of the task. So at least it might hint you that a task was stuck, even if it's not present in the CPU backtrace at that specific moment of the crash. If there was a task that was in the state, you can probably consider that it's a hint, right? So at least it might help. It's not the definitive answer, but it's an extra information that might help in this case specifically. Not sure if you agree with that or not.
Yeah, so we've done, Qualcomm does a lot of RAM dump analysis. So yeah, we take a look at a lot of hung tasks. That's a lot of things that we debug. Looking at the task stack for the task that was hung is usually what we do. I think there's an echo option in the, I always forget that proc, Magic SysRQ, thank you. That'll dump all the task stacks. Usually we can use that. When we get a full RAM dump, what we'll do is we'll just look at all the stacks for every task. So I don't know if we put in a dmessage, it floods dmessage quite a bit. In fact, you might miss some of the tasks or the initial messages of like what went wrong because you've dumped so much into dmessage. So actually the next talk is what I'm gonna give, and we talk a little bit about what we wanna collect in, we call it mini dump, but we're trying to see how it'll fit. I don't want to jump the gun too much, but yeah, I just want to say the SysRQ is something that's helpful for us.
Yeah, I just want to point out that the hung task itself is the victim of something else that went wrong. It's not the cause, right?
Right. Yeah. So usually, yeah. So what we do is we'll look at the stack and then we'll figure out who's holding the lock, and yeah.
So one idea. Sorry, go ahead. Okay. So one idea here is when you're doing this on a VM core, you're probably starting out with a theory you have, and then you go try your next theory, and then you go try your next theory. So what if your panic print was pluggable with BPF or something, and you could plug in a BPF program that lets you print out whatever you want. So the first time you see a crash that gets reported to you from the field, you have no idea. You just see there's a hung task. So then what if you could deploy a BPF program to some subset of Steam Decks or all of them or whatever that says, okay, next time that we have a crash, let's print out this piece of information. And it'll be a very long debug cycle, but eventually you'll be able to get to the root cause, right? So backing up, the more generic idea is like plugging in BPF programs to panic print. The caveat being like, hopefully BPF is in a good enough state at the time of the crash that it'll work. But as long as you like verified it ahead of time, like the BPF guarantees should hopefully be enough that like it's not going to wedge your machine going down in the crash like a panic notifier might.
This is a great idea, a very good idea. Thank you. And I think you said it might be a very long debug cycle, right? But if you factor the amount of devices worldwide and multiple users face that, if it's a crash that is kind of recurrent to some of them, and we have control, we not precisely me, but Valve has control of the software stack, so they can deploy that in all X. So I guess it may speed up the process because it's not the same user that needs to reproduce that. Other users will reproduce, and then we can cycle that. It's a very good idea. And to the point of SysRQ that it was mentioned here, what Panic Print prints in the message, it is exactly the same as the SysRQ. So it's the same function that is called. That's really big dump of information about the tasks. To avoid rotating the log, we increase the log by logbuff something, that parameter, right, that increased for 4 megabytes. Since we have 15 megabytes of free memory in the deck, 4 megabytes is nothing. So that helps to not lose data.
Anyone else? We've got 1 minute here, so that's probably a good time to stop if nothing else. All right. Thank you so much. This is a great talk. Yeah.
Thanks, James. Thanks a lot.
And let me see who's up next here. Should probably have the schedule on. Okay. All right, cool. Easy. That presenter. All right, everyone. Is it 12? Yes, it's 12. So time for our next talk, mini dump. Right? But Elliot is here to give this talk. So thank you, everyone. And yeah.
Okay, so thank you, Jeremy, for teeing us up here. So the talk's going to be, we're going to talk about what Qualcomm does for RAM dump collection. We've had some interest to talk about what we do. We'd like to get some of this, what we do, upstream, instead of having this all downstream, like we've been doing for years. Without further ado, dive into what mini dump is all about. So you can read this, but it's basically the problem statement of pStore. You have dump devices with 16 gigs of RAM. We don't want to send 16 gigs of RAM across the network. It's too much information. There is potentially secret information that users don't want to share. So we want to collect less memory and send that for crash dump analysis. How do I need to move it up? So what mini-dump tries to do is, it's a firmware-based solution. We want to register what we want to dump with firmware, and when firmware detects as a crash, normally you would do a system RAM dump. Instead, you collect just whatever regions you've registered from the kernel or from whatever other subsystem that might be running on your SoC. I think the previous talk was a little bit more x86 focused, we're more ARM focused, so there's other subsystems that, co-processors that we care about. So yeah, mini-dump is there for mostly for devices deployed to an end user. You can't collect a full RAM dump. Crashes could be due to hardware bugs, software bugs. We don't always get kernel panics. I took before the presentation, I took a quick look at the past year of all the RAM dumps that Qualcomm has gotten internally. Only 70% of them are from kernel panics. And of those 70%, a lot of them are just watchdog bytes. So what Qualcomm does is when there's a watchdog byte, we panic the kernel. I think other devices will typically try and let that go to firmware and actually crash the device directly. So yeah, the amount of useful information that you can get out of a limited RAM dump. I'm trying to remember what this talk is supposed to be about. Yeah, the amount of useful information that we can collect from a RAM dump is limited if you send less information. So we're trying to register as much information as we can. So there's a few different options, existing solutions. There's KDump. This slide is going to look very similar to the previous deck. So it's nice. You can use any user space to collect the RAM dump and do what you want to do to send it. There's some problems with it. There's a lot of memory overhead. You need 2 kernel boots to come back to normal operation. You got to boot the KExec kernel, then you got to boot your normal kernel. And only the kernel can trigger KDump. So if you have something that's not a panic, like a knock error, you're in trouble. pStore works really well. It's got pretty low overhead. There's no extra kernel boots. You just reboot and you have this persistent region of memory that you can look at. There's some issues with it that we've kind of observed. There's some collection time overhead, right? You have another console device that copies all those messages from vMessage into the RAM weak region. We want to try and optimize that. If we don't have to do it, why should we do it? Like I said, you need a memory reservation for the randomness region. We don't have to create a memory reservation. We'd like not to. And it's also limited to memory that the kernel can reliably copy before the crash. So in cases of kernel panic, you may not have all the latest and greatest messages from the kernel. So like if you have things in panic notifier path, you can't necessarily get all that information. So yeah, mini dump is there to try and minimize the memory overhead to capture a small dump by sort of shoving it to firmware. It maintains a table of physical addresses and sizes. You don't need to copy message buffers, FPC buffers, or anything like that. And so that reduces collection time overhead. The firmware will collect the region directly to storage. I don't know if anyone here is familiar with RAM dump collection on an SoC, but usually the firmware will collect the RAM dump for you, and then you'll get a reboot back to the device. And then, so in our implementation of mini dump, we have a table of contents, and every table of contents has a list of regions that you want to try and collect. So it's just it's a two-stage lookup. We have each entry usually corresponds to a particular subsystem. And then in that subsystem, like would be one for Linux, you can have a list of regions that Linux cares about. For instance, if you want to collect the log buff buffers, there's multiple buffers, of course, or ftrace buffers, you would register those physical addresses with the framework. And on our Qualcomm devices, on our implementation, when you get the mini dump crash, the device will reboot and collect an ELF, an ELF, and copy that to whatever storage device is available on the chip. Yeah, so this is a little bit more of the same information. It's that same struct in C code format. Okay, yeah. So mini dump. Some of our older firmware implementations have a limit on how many regions that can be registered. So if we try and register, like for instance, every task struct, that's a lot of copying that needs to happen. The number of regions that could be registered. And we're trying to open it up so that way anybody can register a mini dump region. So if, for instance, some new subsystem comes along that we're interested in registering, they can just make a generic call to register their buffers that they want to dump. So Mukesh has been doing all the work for mini dump. He sent V5 the patches. How long ago, Mukesh, was it? A few weeks ago? It was a few weeks ago. You're on mute, by the way.
Almost 1.5 months back.
Okay. A few weeks ago. And for now, we're trying to just collect existing PSTOR records. We don't want to try and do anything too controversial. We're just PSTOR already collects it in a pretty convenient format, so we're just registering PSTOR for now. We've already upstreamed support for mini dump on remote processors, so things like ADSB, CDSB, and modem are already supported. And those drivers maintain a list of segments that they want to dump during recovery. The core dump framework is used when the ADSB or CDSB crashes. You can collect the core dump from those subsystems. The mini dump framework also, like when the whole device crashes, those regions are also collected. So it's kind of like a subset. So here's some of the additional information that we thought would be useful to collect. So it's kind of our answer to PSTOR, what we went to upstream PSTOR. One thing that's been helpful for us is initial boot message logs. So if you want to make sure the device came up successfully, sometimes there's hints in the initial 100 seconds of demessage. We sometimes like to know if there's IRQ statistics. So if you're getting a bunch of interrupts, that tends to be a hint that maybe a device is misbehaving. There's run queue information. Chris, you want to take in the information here?
Yeah, the bunch of information we currently in the downstream we do this. So we are at this moment we are looking for these type of information to be captured in the P store exactly. So currently like MMI tracing, IRQ state, which will help in the IRQ storm kind of use cases, timer summary, which actually the last presentation is talk about already. It does it, but it does it after panic notifier. It print into the D message itself. So those some of the stuffs are already there, but somehow it is not available as the last presentation went, right? So run queue information, what was the run queue, all CPU were running, and then and dump stack of each kind of crash, each core in a kind of crash. So exactly these kind of information we are looking at, and some of them the basic information we are trying to hook with the already existing P store. So all the front end, the P store already captures its like ftrace message, console message. We are trying to register with the minidump, and so that this is the basic aim of the minidump infra to be, and at least the Linux infra we are trying to develop to capture these four front end. And later we are trying to improve maybe P store to capture some of the stuff which is not available. Or this is our aim is going to be. And which is similar to what exactly we discussed in the last, and here and there we will going to improve. And yeah, mini dump is something which is basically not only for kernel crashes, it also covers non-kernel crashes. So basically there are use cases where whenever the system itself, the kernel in itself is not able to run, it is get stuck in somewhere, some transaction is got stuck in CPU stuck, and it is not able to run any instruction. That case, that is where the P store will not, I mean, kernel will not able to run, and suddenly it will crash, right? So Minidump will help in those, even on those situations, it will try to correct random, and whatever the information it captures, whatever the register region at that moment, it will be coming as an ELF. So entire Linux will be registered as an one ELF, and the other, all the other subsystem, like in the last slide we discussed about the remote processor also, all are different indexes it use in a global table. So table of content, and finally each subsystem CDSP modem and apps, APSS we call it as a Linux only. So it will capture one entry in that, and finally all the dump entry, registered entry will be dumped at the type panic. The only overhead it does not have is it does not need extra memory. So because of the in the upstream engagement in the various version, we got to know that hooking hooking with the P store looks it looks very similar, but it has much more capability than that. Given the physical address and the size, it can capture, it can dump anything. So yeah, this is what we are looking for.
Yeah, thanks, Mukesh. So I guess, yeah, what I wanted to sort of get feedback from the community is we want to try and expand how useful Minidump is for other folks. I think PStore works well. It's a kind of middleweight option. It's lighter than KDump. We think Minidump is even lighter than what PStore can offer. And so we're kind of thinking about other stock vendors that are interested in this. Do we think it's interesting for virtual machines? You know, what we're kind of trying to see what interest there is taking Minidump outside Qualcomm. Do we think it's useful? Yeah, it's kind of 15 minutes for discussion.
Oh, I guess I have them both. Well, if anyone wants that, toss.
I don't want to ask those questions. I want to have other ones.
Oh, okay.
Go ahead.
I have my own questions as well, so we're potentially going outside of the intended discussion. But I guess I just wanted to say that this is really interesting because it sounds like the way I understand from your explanation is that you're essentially letting clients, you know, around, or you want to let clients in the kernel register, these are my interesting bits of data to be dumped for firmware, and then the firmware will later on dump it, which is a really interesting way to instead of filtering after the fact, to declare it ahead of time. And you also mentioned some user space stuff. Can user space do that same thing, or is that a kernel-only functionality to register information to get dumped?
Do you mind if I take that? Yeah. So actually, the user space thing he discussed, right? It was for remote processors. So which is
Okay.
already there. So remote processor recovery path will dev code dump path. It will send you. That is the different path altogether. Whether in that case modem will go through a recovery phase after crash, right? So in that case, in the code dump get collected, but the system is still running in that case. But mini dump is not. It's only for kernel crashes. Kernel and plus the non-kernel crashes also it covers. Firmware, hypervisor, everyone can register. So yeah.
So I think, for instance, our initial D message, we have that implemented as a downstream feature where we have a sort of a K thread that runs for 100 seconds, or I think it's a timer that runs for 100 seconds, and it collects the first 100 seconds of D message. I think that would not be acceptable very upstream. I think
But it's so, I want that.
well,
I've wanted that
well,
sometimes, you know?
That's interesting to have it in the kernel. So we implemented it in the kernel because we weren't sure if user space would come up. And if user space doesn't come up,
Yeah.
then you want to have it coming from the kernel as best you can.
Yes.
We could probably implement that as a user space feature where you can just say, hey, here's a file and then you dump, and you can echo whatever you want to echo into it.
That's super nice because servers definitely have a lot of memory that they might waste on or not waste, but use on a print K log. But even then, sometimes high uptime, it's like it's been 2-3 years since we booted up. And it'd be nice to have some of that information.
Yeah.
Anyhow.
Were there other questions? Because I was going to ask something else too to answer. No. All right. Well, I'll just ask my question then. Two things that I want to ask about. One of them was you guys are talking about non-kernel crashes, and that was one part of it. And the second question is you're saying that dev pstore is a higher overhead than mini dump, and I'm not understanding it. Can you elaborate why you considered pstore sort of too high of an overhead? Because to me it feels like it's just one memory region that's set aside, right? It's not like it's thousands of things you have to process.
Yeah. So I mean, if you don't have to set aside a memory region, that'd be nice if we don't have to, right? It's 100 megabytes that you can reclaim and give to users to run an app or
so Chromos only sets aside 1 megabyte for dev pstore, and that's reserved RAM. That's on all Chromos devices. So that's not a very high overhead. And then we have gigabytes of RAM in the system.
Well, so I mean, I don't know how big is log buff usually?
Yeah, megabyte. The log buff usually less than a megabyte.
We usually, how big is it 4 megabytes?
512 KB, yeah, almost on.
Yeah, but I mean, my argument still holds. 4 megabytes on an 8 gigabyte system is irrelevant, basically.
Right.
Yeah, I mean, I will
Especially-
tell you exactly the overhead. I'll try to explain. So overhead, at least we cannot tell this RAM backend is taking this much memory. It is up to the user how much you want to give it. But yeah, let's say example we talk about P message, right? User space logs. For each message, it will be P message writing to the backend. So you are always doing mem copy of stuffs, right? In the background.
Right, but I'm looking at the laundry list of things that you guys are collecting in mini dump, right? IRQ information, MMIO tracing. I mean, there's a lot more stuff there than just one blob of memory.
So
I'm
the
trying to
advantage. Yeah, sure. Go ahead. Yes.
Yeah, I was just going to say, I mean, the advantage here is if you don't have to copy 4 megabytes.
All right.
I know it's not a lot, but.
Okay, it's fine. I just want to understand the
No, yeah,
perception,
it's
right? It
literally
was
as
just,
simple
for me,
as-
the perception
yeah,
was
we don't have to
odd.
create a reservation.
The other one was non-kernel crash sources. Can you elaborate on what a non-kernel crash is? What you guys are referring to there? I think you mentioned Watchdog was one of them. There's a hardware watchdog. Is that a non-kernel crash? Are there other sources of non-kernel crashes?
Yeah.
So I'll go. Yeah. So non-kernel crashes could be anything. Let's say some XPU fault, secure register access can result in XPU fault, and those kind of it will result in a non-secure byte. I mean, it will be. I mean, kernel will not even get a chance to run in that cases. So MMIO tracing, what accesses resulted in that crash can help in the debugging that okay, this register read write can cause that XPU fault. Other kind of crashes could be, I mean, there are other kind of crashes could be the bark. For us, exactly, internally, we manage a non-secure bark is fatal for us. Let's say if any core is not able to run for a certain duration, it will result in a byte, and that cause a RAM dump to happen. So in that case, it can be anything. When core got hung during that, core got stuck during the TLB flush or something, it can be any issue which can be resulting into and we have a mechanism in place. Let's say in certain scenario, this will always result in a byte, and kernel will, because kernel, it's a transition itself, it got stuck and it has to result in a byte. So yeah, those are non-kernel crashes I was talking about.
Okay, so the kernel could be the root cause of those crashes, but you still, because the kernel itself is not causing its own panic function directly, it's an indirect hardware triggering the crash, like a watchdog timer or, okay. I'm familiar with this. I'm asking because on servers that I worked on in the past had a thing called a high priority machine check. So if you were to try to access, for example, an MMIO region, a physical address that was not mapped, it would crash, the chipset would cause a crash that was caused by the kernel, but it wasn't really, it was not triggered by any kernel piece of software. It's the hardware externally triggering this crash. So that's why I'm trying to understand your definition. That's all. Thank you.
Yeah, that's similar.
We have a question from Guilherme up on the online.
Yeah, thanks, Steven. So I found the mini dump very interesting idea. I have a question about the firmware side of it. You mentioned it can write to some, for example, to an SD card. So does it require to have an MMC driver to access the card, or what if the SD card is formatted like ext4, or this case is not supported? I mean, you need a raw SD card exclusive for that.
So basically, currently we support wherever all the images, right, the binaries of the other non-HLS and non-firmware as well as the Linux binaries are flashed, whereas we those as a storage reason, and one of the partition we can reserve it for this mini dump collection, we can call it, and firmware has access to read and write to these partitions, and based on the, so it does not only write Linux region, it also write some firmware region which it wants to dump. So some, let's say, firmware bootloader logs also it dumps. So yeah, it can be MMC, and based on the configuration wise we can set it, right? Yeah. Is that answering your question? You're saying MMC is flashed? No, it's a partition should be reserved for those, exactly. Otherwise it can result, it will not able to write, and it may not collect. Maybe if a brick device can be brick in that case. But yeah, it's a pre-known partition where it will be
Yeah, so there's a dedicated partition that firmware knows to write to. Qualcomm firmware is just hard coded to write to that partition. So that's how it works. Does that answer your question?
I think the room might have been disconnected.
Sure, thank you.
I think you got it, yeah.
I disconnected for some time, I guess.
You can.
In the interest of not proliferating ELF core dumps that look like ELF core dumps but aren't the same as regular core dumps, we've dealt with this a lot. Do you include the VM core info note?
I don't think we do. Would be something we'd be interested to add.
Yeah, so it's just a physical address that you could register, except you would have to, it wouldn't be a regular ELF segment, it would be a PT note segment with a little bit of extra metadata. And that'd make it easier to use like pre-existing tools with it.
I see.
But you probably need to tell the firmware like this needs different metadata.
Yeah, we'll have to, let me talk to you about that offline so I can figure out what we need to tell our
I mean, you guys probably have your own tooling that doesn't care, but if you want to use like other tooling, it might expect it.
Well, we'd like to use tooling that's more available because we don't like maintaining these things either. Go ahead, Doug.
How rigid is the firmware with respect to the kernel version, right? So I think is it just getting the regions of memory and storing them? So it's the kernel is in charge of essentially describing like what regions of memory it would need to save for demessage, and there's no like hard coding of the demessage structure in the firmware or anything.
No. So so you have to know which or which kernel version that dump came from to know like the structure layout. Is that what you mean?
Yeah, yeah, essentially.
Yeah,
So
you have to
the
be able to map the kernel version to the dump.
We at I think we are also trying to capture the Linux banner exactly in the ELF. So as a part of ELF, right? Which crash belongs to which kernel version. So that is the patch set. If you go through it, one of the patch is also trying to capture in Linux banner as well. And also the one thing exactly in the last talk we discussed about the reserve memory of pstore, right? That also we are covering in the patch series. In the last talk, Girham was talking about, right? There is no kernel parameter exist exactly to reserve RAM ops region. So yeah, that was also the series was capturing. Yeah.
Yeah, Hari had a question. If the primary motive with mini dump is to avoid having to reserve memory that is needed for a full K dump, yes. Yeah.
Yes,
that and to be able to run dumps that aren't triggered by kernel panic.
Also, I guess the mini dumps probably allow not having warm reset. I know when we did Qualcomm Chromebooks, we had to specifically jump through hoops to get Qualcomm to let us do a warm reset. They had to make up what they called mission mode warm reset because in their mind, rebooting and preserving RAM was not something that you did. And so on all other SoCs, it generally works okay, but Qualcomm seemed to have a policy about really, really cold rebooting on every reboot. And that kind of broke pstore. And so I would imagine that writing to something like eMMC would also work around that requirement.
I had a question about, you mentioned that you're capturing the stacks of hung tasks basically. So is that something that you you patch the kernel or register a hook or something on a hung task? You register the physical memory region of the test struct, or how are you doing that?
I think for what we do is we do that.
No, hung task we don't collect. Actually, these the slides which were mentioning what we are looking at exactly, those information for debugging information. At least the minimal information we are looking at to be captured for a debugging an issue. Not 100%, but it's somewhat some extent.
Sorry,
Yeah,
so you're
hung
saying that's
task,
something you want but don't have implemented yet?
Yes, yes. We have a hooks in place somehow that I mean think we were not capturing exactly the your hung task thing. Hung task is not mentioned here, but we actually we were talking about, right, that there is a parameter exists if you write W to CSRQ trigger, right? That will flood that message. We could have an idea about we can reserve on a region where some extra buffer where it can we will reserve that memory with the mini dump and we'll redirect that entire buffer entire text content of the to that buffer. So and because it is registered with the mini dump, it will automatically capture.
Thanks.
So instead of flooding the D message, we can have a separate buffer and register with this. So, but exactly this is a downstream thing, right? We are looking something which is we can upstream and maybe add it in a pstore if possible.
All right. I think this has been some really excellent discussion. Thank you for this presentation. It's really cool to have these contrasting approaches and having everyone in the room to talk about it. So thank you. Yeah, no problem. In a minute and a half or so, we'll have our last talk. So stick around if you want.
Fallen a few times.
We'll give people a moment to step in here.
Oh, it fled already. That was sad. Tell me it fled already.
All right, we'll start 30 seconds early. That sounds good to me. So yeah, our last talk, but not last, but certainly not least, we have Kernel Live Dump with Lucas. Please go ahead and take it away.
So, hello everyone. My name is Lukáš Hruška. I work for SUSE as a kernel live patching developer, and I would like to show you my small project, Kernel Live Dump, and hopefully get some feedback on it or tips how to solve some of my problems I currently have. So, what it should actually do? Live Dump should provide some way how to create a consistent image of the kernel memory without stopping or restarting the machine. This would be useful, for example, for cases where we are trying to debug some complex issue which is running only on some machines which are on the production and also running some high-level services. So the creating some KDump and restarting machines is not the option. This feature was already introduced in 2012 by Yoshida Masanori as a proof of concept of this feature that is also working. And I used it as my baseline and revised it to version 6.2 and started working on it. So this is also a way how to thank for his work on it. Now let's take a look on some summary of the features and compare them with the current state. Restart is, of course, currently not required, so that's one good point. We are using the copy on write technique. The consistent state is questionable because there's still one problem with VMAP areas, so this is going to be discussed later. Currently, I support only x86 architecture, but I would like to extend this support in the future. The Live Dump supports multiple possible targets, but currently there is only one as an example. And the output is actually supported by most of the crash debugging tools because the output is same as the VM core format. The implementation is separated into three parts, where only one is architecture specific. It's the write protect part, which makes sure that the memory is all read-only and unlocks it after it's making sure that the handler which is provided during the initialization phase saves the memory before opening it per each page frame, which is our main unit in this case. Then we have Live Dump core, which is just a wrap up of everything, holding it together, handling sysfs attributes work, and also it makes sure that we are using the correct Live Dump handler for actually specified output path. Then there is one of the implementation memdump, which just simply use the block IO requests to save those data on the ROM block device. To understand it better, we take a look more closely to the write protect. How does it work? There's 4 phases, and to keep a track about this current state, it needs 2 bitmaps and 3 flags inside the page table's PT record. The PT I'm saying because currently for simplification, I support only 4 kilobyte pages, and it's just for now. It will be in the future extended. The 2 of the bits are obvious, which are required. It's the present and read write. And then I am using the software 1 bit, which I'm using as a backup of the previous state before the write protect started. This way, I have handled those cases when I have more than one virtual addresses accessing pointing at the same physical address. So, and all of them could have different protection. So this way, I will definitely restore the previous state correctly. Then one of the bitmaps is informing if this page frame, if the write protect is interested in this page frame. And then the second bitmap is a subset of the first one, indicating if the page frame was already saved. Now take a look at the phases. The initial phases just save the provided handler, which then calls on each page frame. Then it splits all the pages to 4 kilobyte ones, and in the end, it just initializes the bitmaps. Then more interesting one is the start phase, which starts the stop machine state, in which it first checks the E820 module, which just says us which memory is reserved and which is usable by the system. After that, we save all the sensitive pages, which contains, for example, all the page table structure, which can't just page fault during accessing them or changing them. Then we enable our own page fault handler, which we require. And in the end, the rest of the addresses are just traversed using page fault and set to read only. After exiting the stop machine state, we get a lot of page faults in our custom page fault handler. We solve them by first checking the error code, if it was a protection error, also write operation, and from the kernel. If it wasn't, we just let the original page fault handler to handle this page fault because it's not something which we should care about. Then there is a mistake in my slide because I try to optimize the conversion from the virtual address to the physical address by just in case of having like direct map address, to just do the subtraction of the page offset and then just shifting by the page shift. But first, I unfortunately need to call the lookup address anyway to get the PTE record to check if the previous value of the read-write was actually writable. Because if it wasn't, this is just classical protection error, which I wasn't like made for write protected process, but the original page fault handler. Then when I have the page frame number, I check if the write protect is even interested in this page frame. If it is, I check if it was saved already. If it wasn't, I call the handler which was provided, and then in both cases I unprotect this virtual address. Now I have handled all those accesses, like tries to write into my memory, but then I have still read those kind of parts of memory which were originally read-only or were writable, but they are not that often like changed. So I need some sweeper, as I call it, which just travels through the all memory, checks if it was already saved, and it wasn't, save it and unprotect it. Then the last phase is just an uninit. We just restore the memory and set the software bit again to the 0, so it can be used by other modules or solutions. Now, when we understand how the saving is being done, let's take a look at the problems I'm starting to have. One of the biggest is the queue size problem, where memdumps handler is currently saving every page on the queue, where we have more than one queue. We have 4 queues. 2 of them are like a list of free pre-allocated pages to be used to save, to back up those faulted pages. And then the second 2 are like those which should be currently processed because they are filled with some useful data. Then we have K-thread, which is just processing those queues and trying to save them on the block device. The reason why we have 2 of them is because we are separating those calls from the page fault and those from the sweepers, because they have different priorities, because we can't just sleep longer on those page faults because we are just traversing the memory and let the system wait just because of that. Now the problem is what should be the size of the page fault queue. Because during the stop machine state, we are first filling the queue with data of those sensitive pages. And then after exiting, there are also some data structures used by the BIO itself, which are currently locked. So they are also generating some page faults which are filling this queue. And if the queue wasn't big enough, we would just simply have a infinite loop, which would just crash the system, and we don't want that. My first idea would be is to create some calibration phase, which would normally write protect the memory, write to the some variable where we are sure that it's also write protected, and then using tracing, wait for the completion of the write on the block. For example, in this case, block device, where in this case would be this trace point block request complete. Then I would check what was the maximal count of the used preserved pages, and then I would just multiply it with some constant, so we are sure there is still some reserve for the other page faults, which would be from other threads. The other option would be also to unlock as many page frames which are being definitely used by the write operation, because in this case we shouldn't rely on correctness of some technology which we are using to save this live dump. So we should, in case of we would for example, debug the bio, which we shouldn't use the bio to save the dump because we can't be sure it's already correct. So we don't care if we would lose those page frames. Also, another way how to somehow optimize it would be to have more variants of the page fault handling, because not every time we need like 100% consistent state. We could have variants which would be 100 consistent variant, but it could have some possible performance impact, where we first could try to allocate more and more pages for the page fault queue until there wouldn't be any memory, and then have the active waiting inside the page fault handler, which is what we don't definitely want. Or we could have a possibly inconsistent version, which would just throw away the data in case of the queue is just full, and somehow flag it inside the output, but it would require some modification of those crash dump debugging tools. Also, what I was thinking about could be a version where we would have 100% consistent variant with minimal performance, but it could like just crash and don't complete, which would be in the case that the queue is again full. Now, something about now the work which is still in front of me. The VMAP area, the only problem currently I have is the synchronization problem, because all the other memories are using either VMAP, is it mutex or spinlock? I'm not sure now. No, it's a semaphore, and then there is a spinlock for the page type abstract. But the VMAP, if I understand correctly, you can correct me if I'm wrong. There are two spinlocks, where one is for the free area and one is for the use area. And to be able, yeah, you can correct me.
Oh, no, I wasn't going to correct you on that. I was just going to mention that Dragon and I believe Crash will both work just fine without you preserving the VMAP area, as long as the corresponding physical addresses are, as long as the memory still gets preserved in the direct mapped area. And we'll just walk the page tables ourselves to resolve the virtual addresses from the VMAP area. So is the problem that that your page fault handler can't figure out which physical address the VMAP corresponds to, or is it just that you want to have the virtual address to physical address mapping in there?
Well, sure, maybe we can discuss it later after the other
Yeah,
presentation.
If you can avoid having to deal with that at all, it'd be nice.
Yeah. Okay, so the options would be to either export those pinlocks, which I know it's not that much welcome, but the other idea would be to have something similar, which is to the page walk, where we would have a VMAP walk, which would just require the handler to be provided, and then first it would correctly log those pinlocks which are required for the accesses of those memories you want to access, and then it will call the handler you want to call. Other thing is that I'm currently using the stop machine state, but stop machine state is not that instant thing because it's just scheduling high priority thread. So we still are waiting for the scheduler to schedule it, and the interrupt will be much better thing because we want that exact instant when we press the enter that we want the live dump to be created. Then I would also like to do some analysis of the impact of splitting those pages because I know there should be some TLB overhead, but I don't know how big it would be. And then either to have some huge page support where I would have for each size of the page a different queue, but then there will be other optimization problems, how to reuse those bigger queues and so on. Or to have a page table restoration where I would first create the backup and then track all the modifications being done during the run, and then just somehow restore them back with the already created backup. And also, of course, I would like to create other target storage support, for example, to create a file instantly or to just send it somewhere through the network. So thank you for your time. Any question, ideas, tips? I will be happy for anything.
Yeah, I have a couple. Sorry, I'm always asking questions here, but yeah, one thought I wanted to ask, do you do any dump filtering like make dump file would? Because that could reduce a lot of your workload and performance issues, right?
Currently, I'm not, but this is a good idea because sometimes we have only some quick caches or data which we don't need. So
yeah, 95% of the time you don't care about user space data, page cache data, private cache, stuff like that. So if you can get rid of that, then your page fault handlers can let user space move on in a lot of cases.
It will also help with the problem with the queue size because there will be so much traffic.
That too. And on your queue size problem, I had another thought. One thing that the kernel does with the memory allocators is that it has kind of a reserve emergency amount that it can use for certain cases, like min-free kbytes, I believe might be part of it. But essentially, have you considered having a flag you can set where I'm already in a page fault handler? And then if you get into a recursive page fault handler because of, say, the block device, the block device is trying to write and you get another page fault, you can check that flag. And if it's set, then you can say, oh, wow, I need to use some of my emergency reserve queue space here and go ahead and use that. And then if you're not in that recursive situation, then you would never use that queue size or that queue region.
Well, again, I didn't think about it, and it's really a great idea. Thank you.
Yeah. Oh, awesome. Other questions, comments?
One thing I was just curious about was the software bit. Do you know what else uses that you might conflict with?
I checked it in the upstream, but there was no use of it currently. But there might be some external modules which are using it. So
okay.
Currently, it's free.
Alrighty. Well, it looks like we'll have a few minutes to give back to everybody, but we're all probably going to be up here at the front. So thank you again, or thank you for the first time and again for your talk. Yeah. And thanks to all our presenters here. I really appreciate it. This is a really successful first micro conference for us. Thanks. Cool idea. Oh yeah. Honestly, a lot. Good work.
How do you like running your program?
Not bad.
Hopefully, you had enough information.
Yeah, that's it.
If I understand it correctly, is that what I was trying to do was to correctly lock all the memory and then just walk through the direct map because it makes sense that I'm just saying everything in case of
I know there are some features coming which we could make sure the bucket was that.
Yeah, I'm trying to save batteries.